Hey everyone, so today we will be digging into PyTorch. This is going to be an introduction to get you more or less knowledgeable of all the different things you can do in PyTorch, just to give you a quick introduction so we can really start digging into more advanced models in future videos. So let's go ahead and just get started. So first of all, PyTorch is basically NumPy. So if you have used NumPy, it's effectively Python's most popular array manipulation tool. You already know most of the functionality of PyTorch, which is great. PyTorch, though, has two key abilities that NumPy does not have. Number one, you can do GPU computation. Now, there are some packages out there that let you do this, like CuPy and a few others that also let you do NumPy-like GPU computation and all that, but we can move our data to the GPU, which is great. And it also does something called automatic differentiation, which effectively powers neural networks, specifically the back propagation, which we will be digging into soon enough. So what are the prerequisites? I expect that you've seen NumPy a little bit and you know what a for loop is. There are some classes, like we need to write model classes in PyTorch and just the way that it's set up, but it's pretty easy and you don't really need to understand all the fancy like class-based things that we need to worry about. So it's no big deal. What math do you need to know? Well, most helpful is knowing linear algebra, calculus, probability statistics, and optimization. I'm not going to dig too much into this stuff. I'm going to try to keep it as math light as possible, but there will be some places you'll see today where we will be doing some of the derivations just so you get a feel for how some of this stuff comes together. And so there's also obviously lots of stuff that you can learn outside of neural networks, which seems to inspire a lot of the interesting architectures we have today. But for today, we're obviously not going to worry about any of that. So as we're starting out, we need to define a tensor, right? So what is a tensor? A tensor is basically a bag of numbers that's more than two dimensions. So let's just start from the beginning. A vector is just a list of numbers, right? If you have a vector, it's just one list of numbers. And a matrix can have two dimensions, right? You have maybe a height and width. So an image could be a matrix, for example. If we look at this red square here, this is a 4x4 matrix of numbers. The moment we leave a two-dimensional grid of numbers to maybe 3, 4, 5, however many, that's when we typically call it a tensor. And so a color image, for example, is a tensor. Why is this? Because each image has a height and width for, in this case, it's a 4 pixel by 4 pixel image. And there's also a depth channel. Now, it's not really depth, it's color depth, because all color images, at least in the way we typically represent them, is RGB, red, green, blue. So we have three color channels by 4 by 4. So the shape of this tensor would be a 3 by 4 by 4 tensor. And it's as simple as that. So we now have a 3D matrix, and this is why we call them tensors. We're going to go ahead and try to create some tensors here just so you get an idea of what's going on. So I've gone ahead and just made some of my imports here, so don't worry about them too much. I'm actually not sure we're going to use all of them, but we will be using most of them. So let's go ahead. So we're going to do data is 1.0, 2.0, 3.0, right? So what I've done here is create a simple list, and let's actually make it a little bit bigger. I've created a simple list of numbers, and our tensor is going to be torch.tensor data, right? So if we look at this, this is actually very similar to if we had done numpy np.array data, right? This is a numpy array, and you can see it says an array here. A tensor is a tensor. So there we go. We now have a tensor, and it's as simple as that. And this is a 1D tensor, and just like in NumPy, right? You can do dot shape, and it'll give you that this is a length 3 tensor. So no big deal there. We can also make a two-dimensional tensor. So we can do data is, let's just do data. So this will be a, let's call this 2D data, or let's see, whatever, multi-dim, let's call it multi-dim data, right? Multi-dim data is going to be this, it's a list of lists, but if we do, again, torch.tensor on this, and it doesn't actually matter if you do uppercase T or lowercase t, but either one, now we have a two-dimensional grid. So we have 2 rows and 3 columns. So if we do the shape here, dot shape, it'll say it's 2 rows and 3 columns. So that, very simple. We kind of have these things. And so again, this works almost like NumPy. There's not too much to worry about here in terms of the functionality of the tensors. One important thing to be able to do is to actually create random tensors. This is just so, well, in some architectures, we actually need some type of randomness, but it's also a good way to debug your models. And so what we're going to do here is very simple. We're going to do rand is torch.randn. So randn is sample from a standard normal distribution. And let's say I just say 2. So then our rand is just 2 random numbers selected from some standard normal distribution. You can see every time I sample, it'll give me different things. If I just done rand instead of randn, then it would be uniform. You can see the numbers are now always positive between 0 and 1. Doesn't matter. It's whatever distribution you want to sample from. So randn. If we do 2 by 3, it'll give me a 2 by 3 grid, right? 2 by 3. So the two rows, 3 columns. What if I do 2 by 3 by 3? Now I have 2 tensors. And each tensor is 3 by 3. So if we look at this example above, right, this was a 3 by 4 by 4. So let's do that. So let's do a 3 by 4 by 4. And so this is showing, this would be my, obviously it's not actually, it's just fake data, but this is my R channel, G channel, B channel, and each channel is 4 by 4 in size. So this is kind of what an image would look like. So yeah, that, very, very simple, nothing too crazy here, but the important part is this, the AutoGrad system. And this is exactly how PyTorch basically does all the derivatives and whatnot. And we'll be going into why we need to take derivatives and all that in just a little bit, but let's first start with the basics. So we're going to take this example here and kind of just work it out a little bit. So what I picked, so let's go to here. Okay, good. So what did I pick? We have 3 times x plus 2 whole squared, right? This is my f of x, right? No big deal. And what we want to do is find the derivative of this function at a specific value. So how do we find the derivative? The f prime of x is equal to 3 times, right? Just like always, the 2 comes out in front and we subtract 1. So 3 times 2 times x plus 2, which is 6x plus 2. So this is the derivative of this function, nothing crazy, right? So if I wanted to find f prime of 1, right? So what is the derivative of this function at 1? This is going to be 1 plus 2 is 3 times 6 is 18, right? That's the derivative of this function at 18. I'm assuming that you know what derivatives are and whatnot. We'll dig into some of the like the geometric interpretation of derivatives a little bit later because it is important. But for now, this should give you an idea, right? This is how we take the derivative. No big deal. So can PyTorch do the same thing? And that's basically the big question here. So we're going to do is create a random tensor. We're going to do x is equal to torch dot ones, and we're going to do 1. And as expected, right, it's just a tensor with the value 1 because we want to evaluate this at 1, right? When x equals 1, we want the derivative there. Okay, no big deal. And so now we're going to do y is equal to x plus 2. And then z is equal to y squared times 3. Right? I've taken the function and composed it into a couple. You can also do it all in one line. I'm just showing how this works out in pieces. So we have x is 1. We then take 1, add 2 to it. Then we square that whole thing and multiply it by 3. Right? That's our output. And so z should equal to 27. Right? The output when we plug x into this thing, it'll be 1 plus 2, 3. Squared is 9 times 3 is 27, so that's correct. Now what we want to do is compute the derivative, right? So if we try to compute the derivative now, we're going to see a runtime error, right? It's saying elements of tensor do not require a grad and do not have a grad function. So basically, in this implementation, there's no logic currently. PyTorch hasn't hasn't started doing that automatic differentiation and gradient tracking and all that just yet. And why is that? Because we actually have to enable it. So we need to enable it by doing requires grad equals true. This makes sure, so let's comment this out real quick. Then you will see here that 1, it's no longer just tensor 1, but that it's tensor 1 requires grad equals true. This means when we do y, and this is why I broke it up, just so you could see each kind of function, y is going to be 1 plus 2, which is 3. So y is 3, and the grad function is add backwards. Why is it add backwards? Because we did a add. After that, z is going to be 27, like we saw before, but it's multi backwards, right? These are basically multiplication operations. So that's the only reason I broke it up like that. And now we can do z dot backwards. And now it definitely should not throw any error. So we have now computed the gradient. Now, how do we actually see this gradient? Let's do x dot grad. And there you go. The gradient on x is 18, just as we expected. Right, so no crazy math here. It is pretty cool that it's able to do this, but let's dig in a little bit to see how it does this. So what we're going to do is we're going to take this function that we did and compose it into the computational graph. Now, PyTorch may not do it exactly this way, but this is pretty close to what it's probably doing. So what are we starting with? We have here a, let's do a better circle. There we go. We have an x, right? This is my x. And what we're going to do is add 2 to it. So here we go. We're going to add 2. And these things are going to come together and do a sum operation. And it's going to produce, let's say, tensor or some value a. Like, let's just pretend. And then we have, see how we do x plus 2 whole squared? So really we're doing x plus 2, but we have to do x plus 2 a second time, right? So we're going to do another 2. And then these two are going to again come together and do an add operation. And then this is going to output, let's say, b. And because it's x plus 2 whole squared, that's really just x plus 2 times x plus 2. So these two things, a and b, can now come together and do a multiplication operation. And then the last part is we need to multiply this whole thing by 3. And so that will be this right here. We're going to multiply this by 3. No big deal. Another multiplication operation. And actually, let's make this a little bit clearer. We're going to say the output of this a times b is c. I'm just going to give him some temporary variable names just so it's clear. And then we're going to multiply these two things together. Another multiplication operation to provide y, right? My output, or f of x, whatever, doesn't matter. And so what we need to do now is backpropagate on this graph. Now our goal is to find dy dx. So really all we need to do is take every direction back to the tensor of interest, x, right? We want to find gradient on this. And this, what I'm about to do, is not fancy. It's doing exactly what we saw above right here, but we need to somehow operationalize it and make it work out. And that's what PyTorch does. So let's just start. So let's do this first portion. So we're going to do y. Y is equal to c times 3. So 3c, right? So this is me starting my backpropagation, right? Of how am I going to compute this derivative? And we'll talk again later why these derivatives are important, but this is just to give you an idea. So this is my first step of backpropagation. Y is 3c. Now that I have y equals 3c, what I need to do is, how does y change when c changes? So we're going to do dy dc is equal to 3, right? If y is 3c, then dy dc must just be the constant, 3. So that means we are pushing back a gradient here of 3. Next, we have to do this next step. So how does this change? So c, if you remember, is going to be equal to a times b. A times b. So we have two variables here. Here we only had one, and 3 is not really a learnable parameter, so we only have to take the derivative with respect to c. But now we have a and b, so we need to do dc dA, which is just equal to b, right? dc dA is b. And then similarly, dc dB is equal to a. Okay, so let's do that. So we're going to do this step. This is going to backpropagate a b, because dc dA, as we saw, is b. And similarly, this is going to backpropagate n a, right? dc dB is just a. Great. Now let's do each of these branches alone. So we'll start with the top one. So this is going to go back again. We're going to backpropagate. This is again a sum operation. So what is this? A is equal to x plus 2. That means dA dx is equal to 1, right? Derivative of this function with respect to x is just 1. Okay, so then this is just, and let's actually just do it on the top. This is just 1. And for the same reason, this will also be just 1, right? B is just x plus 2, right? So again, we can do it real quick. B is equal to x plus 2. So that means dB dx is equal to 1. And this sets up our computational graph. Now, the important part here is chain rule, right? What we're going to do is dy dx is equal to every portion of c. So we're going to do dy dc, dc dA, dc dB, and a and b add together to give like the full derivative, and then we are back to x. So just so it's clear, we can now start multiplying our gradients together. So dc dy, or dy dc is 3. So dy dc is equal to 3. dy dc is 3. And then dc dB, or dA, let's do that, dc dA is equal to b. This means dy dA, right? dy dA is equal to 3b, right? By chain rule, right? Because dy dc times dc dA gives me dy dA, which is just 3 times b. So up to here, so here it's 3. Here it'll be 3b. Similarly, dy dB is equal to 3 times a, right? So we're at 3a here. And so we continue. I forgot to draw this arrow here. And so then 3a, so 3 backpropagates here, 3b now backpropagates here. And now we're just doing, we're at dy dA. Then we have dA dx is equal to 1. And so dy dx is equal to 3b times 1, right? We're just accumulating. So this is 3b times 1. So this here is again 3b. Similarly, this here is 3a. And the important part to keep in mind, right, when we're doing this is all these nodes that have multiple inputs. You can see how x has multiple inputs. We need to accumulate them. We need to add them together. So the derivative on a, so dy dx is really equal to 3a plus 3b. And that's it. So how does this turn into what we saw up here? Well, we know exactly how to do this. We know a is going to be, we saw a is x plus 2. Okay, fine. So 3 times x plus 2 plus b is also x plus 2. So 3 times x plus 2. And we can just rewrite this as 3 times 2 times x plus 2, because we have it twice, which is just 6 times x plus 2, which is the same thing as we had here. So the computational graph, all it's doing is every time we backpropagate, it looks at the operation. This is why you saw the mul backward, right? And this one would be an add backward, right? So at every operation, we know exactly how the gradient flows there. And we just compute this gradient flow at every single step. And then we just multiply those chains together. And at any node, where we have multiple inputs, we just accumulate it up. And this is exactly how the AutoGrad system is working. Nothing crazier than that, basically. You could rewrite this in a bunch of different ways, but this should give you some intuition. I'll have a future video of actually re-implementing the AutoGrad system. There's a video by Karpati on I think it's called Micrograd, which is pretty incredible. So I would take a look at that. It's basically a fancier version of what I just drew out here. So that should give you an initial idea of the gradient system, right? Of this automatic differentiation. Now, what we're going to do is start with linear regression, right? Linear regression is always a good example to start with because it's easy to define, and it'll let me kind of explain a couple things that go into into neural networks. So let's go back again. Let's scroll down a little bit. What we're going to do is define a little bit of linear regression. So linear regression is this. We have some axes. That's a terrible axis. Let's draw with the straight line maybe. So there we go. We have some axes, right? Just like that. And what we have is some points, right? Some points in our data. And each of these points is a x, y coordinate. Nothing fancier than that. And so what we need to do is our input, right? The input to the model, this is the input. The basically we have these xy pairs. We then have our model. So how do we define the model in linear regression? Let's just move you aside a little bit. Okay, good. So if you've ever seen linear regression before, it will look something like this. Y equals mx plus b, right? So basically we're taking some line. So let's just draw a line here, something like this, right? We have a line that defines the the trend in our data. And so what are the two things that make up a line? Well, the first one is the slope, right? The rise over run, the M, it determines the tilt of the line effectively. And then we have the B, a translation task determining kind of the height of the line with respect to the x-axis, right? So it can go up and down. So using these two things, M and B, we can effectively just fit a line to our model. And step one is we want to find the line that's best modeling our data. So the first question is, what is best, right? How do we define best? And this is where we define something known as the loss function, right? The loss function. In the case of linear regression, there's actually a ton of loss functions we can use, but the most common one is mean squared error, which will look something like this. It'll be the sum of I equals 1 to n, or I equals 1 to n, and it's going to be y minus y hat squared. So y hat is my predicted value, y is the true value, and we're doing the square distances between them, adding them up, and then doing a 1 over n, so it's a mean. So what does this look in practice? Basically what we're doing is for each of these points, we're grabbing these distances right here, all of these distances, something like that, right? And for each of these distances, this is distance, we're going to do d squared, and then compute the d squared for all of them, right? For all of them, add them up, and then divide by n, effectively finding the average square distances. Nothing crazier than that. So let's quickly draw another line. So we're gonna create a copy of this, put you right here. Right, so what I'm gonna do is erase some of this. So there we go. Oops, erase all point, it's fine. All right, no big deal, that's fine, I'll just draw the points back. What we have now is, let's put those couple of points back. There's one here and maybe one right here. There we go. That should be fine. All right. So let's draw a different line. Let's draw this one. Right. In this line, we have new distances, right? We have this one, this one, this one, whatever it may be. So these distances. And we would assume, right, by looking at the picture, we can see that this, if we took the average of these d squares for our entire data set, like all of our inputs, this one's MSE should be greater than this one up here, right? This one's MSE, so this is MSE2 is greater than MSE1, right? So this one has MSE1, and this one will have MSE2. So this one's mean squared error is higher than this one, meaning this is most likely a worse model compared to the one up here, right? So this is our loss function. It quantifies how wrong we are, and really it lets us determine how do we define the best model, right? The best model. Great. So now that we have that, let's go ahead and expand it out a bit. So we can actually do this directly. I'm not going to do this derivation specifically because I think it's not as necessary for us, but how do we do this? How would we solve for it? Well, our goal is this. We have a cost function, right, that looks kind of like this, right, some cost function. And our goal is to find m, right, the best m. And here's the cost. And so the cost function is basically find the m that minimizes the cost, right? Find the m that minimizes the cost. Well, in calculus, you learn that if you have a function, take the derivative and set it equal to 0, assuming the function is concave like this, right? Assuming it's concave, or basically you're guaranteed that the minimum is at the bottom. If you have a function, take the derivative and set it equal to 0, that will automatically provide you the min value, right? That's one of the properties of a derivative, which makes it very convenient. So how do we do it? Well, this is our function. So we have 1 over n. So our cost is equal to 1 over n sum y minus y hat squared, which we can also rewrite as 1 over n sum y minus mx minus b, because y hat, right, this is y hat, our predicted, our y hat is just mx plus b, so we have this squared, right, these two things are equivalent. So then we can do d cost dm and take the derivative of this and set it equal to 0, and this will provide me the best m for this model that'll minimize this entire function. Similarly, we can do dc db, right, for the intercept and set it equal to 0, which will again provide me the best b. And you can solve this, and it's not very complicated. There's a little bit of like fun manipulation you get to do, but this form is actually not super helpful for us, right? The reason being, this is a simple linear regression with just one input x. But what if we had multiple, right? So let's scroll down a little bit. Right now, we have y equals mx plus b, but what if our function was this? Y is equal to w0 plus w1 x1 plus w2 x2 plus dot 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 plus wm xm. This means our input x has m inputs, right? There's n variables effectively. This would be the same as like having a CSV file with n features that we want to pass into a model, right? M columns. So we have m inputs and we have an intercept, which means we also have m weights, w1, w2 up to wm, that correspond with each input. Right now, writing it like this over and over again is a bit of a pain. So we can rewrite this in kind of its matrix form. So let's set x, our data, or x is going to be 1, x1, x2, dot, 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 x, m in this case. And our w is going to be a column vector, and this is going to be w0, w1, dot, 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 wm. And so if we do x, w, well, that'll provide us w0 times 1, w1 times x1, w2, dot, 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 all the way up. So it'll provide the same thing, right? xw is basically our form for this entire regression. So our final thing is y, right? We can now rewrite it like kind of like this. Y is equal to wx, or xw, sorry, xw plus an error term, right? An error term. So again, let's redraw this a little bit, right? So our data looks like this. Here's our line of best fit, or a fit. And so our y, our true y values, is going to be wx, which is this line, right? This line is this, w0 plus w1x1 plus dot dot dot. Obviously, there's more features. I can only draw up to 2 here, but it's this line plus some error, right? This error is the difference, right? This random error term. And our goal is to minimize error, or specifically mean squared error. So we can rewrite this as error is equal to y minus xw, right? Just swapping the sides, no big deal. And our loss is going to be error transpose error, which is just mean squared error, right? So instead of just doing error squared, we have to write error transpose error, as that's the typical matrix form. And that gives us everything we need, right, to set it up. So our goal is to minimize error transpose error given using W, right? Using W. W are the little knobs that we can change, right? The W is basically the slopes and the intercept, and we can change them to minimize some error. So this is the same as saying we want to minimize W for y minus xw transpose y minus xw, right? Nothing too crazy here. Right? We're just kind of plugging things in. And so how do we find the minimum? Well, we take the derivative. Taking the derivative of matrices is never fun, especially when you have the product of them like this. So let's simplify our life a little bit. This is really just a minus b whole squared. It's just the matrix way of writing a minus b whole squared, which we know is a squared minus 2ab plus b squared, right? So let's just write that out. So this is going to be equal to the min w, and this will be then, we can't write y squared, it'll be y transpose y minus 2. What is a? A is xw, but there's a transpose on it, so there's a rule. So xw transpose is the same as w transpose x transpose. That's just one of the matrix rules. So it'll be minus 2 w transpose x transpose, right? Because it's xw, but there's a transpose term here. And then we have the y, so that y is there. And then plus b squared, which is going to be, again, xw transpose times xw. So it'll be w transpose x, xw, right? This is our mean squared error, right? Nothing too crazy here. Now that we have this, we can take the derivative, right? Now, first of all, we're taking the derivative with respect to w. Notice that this term doesn't even have a w in it, so we can just ignore it, right? It doesn't matter. It's just a constant in terms of the derivative. So we're really just taking the min of the second two terms. So dw is going to be of negative 2 w transpose x transpose y plus w transpose x w. Again, whenever you get confused about matrix derivatives and stuff like that, just think about it in the normal terms, and then we'll go from there. So this is really just w times x times y. So if you're taking the derivative with respect to w, it's just whatever's left over. So that's going to be equal to negative 2 x transpose y. And for the second term, right, this is really just doing w squared and x squared. So w squared x squared, whatever it may be. So taking the derivative of that, it's just 2w x squared. But we just have to write it in the matrix form. I always look at my, I have a derivative table that I always look at that's helpful for this stuff. So this will be plus 2x transpose x w, right? So there we go. And we can just set this equal to 0. And so then we can do, just rearrange x transpose y is, the 2's cancel, right? Because we don't really care about them. It's constants, it's equal to 0. So x transpose y is equal to x transpose x w. So our w is equal to x transpose x inverse x transpose y, because we need to take this thing here and just move it over there, but you can't actually move things over, so you have to multiply by the inverse on both sides, and there you go. We now have our form. Linear regression is especially nice because it has something known as a closed form solution, right? What does that mean? Given your data x and given your output y, we can directly compute w. Now this assumes x transpose x is full rank and invertible, right? There are cases where it's not invertible, so you have to use something called a pseudo inverse and stuff to deal with it. We won't be going into too much detail there, but this should give you an idea, right? This is effectively the derivation of linear regression, and I just did it just so you have it. It's important to be able to see these things because this derivation will come in handy when we start doing fancier AutoGrad calculations in future videos. So I just want you to have it. So there you go. So now let's go back to PyTorch and actually implement it. All the stuff I just talked about, all these fancy things, we don't really have to think about it too much. First of all, Scikit-Learn will kind of do this for you. So let's first create some dummy data and work with it. So we're going to do x is np.arange, 10, 0.5. What did I miss? We're going to go from 0 to 10, sorry. 0 to 10. 0.5. So we just have a bunch of numbers here, equally spaced out, no big deal. And we're going to do, let's say y is equal to 2 plus 3 times x. Right, so that's my output. And so we can do plt.scatter, x, y, plt.show, and nothing fancy, right? We have a line, the intercept will be 2, and the slope will be 3. Okay, good. So yeah, that sets it up. And now what we want to do is fit a model that can predict that. Now this is a little bit cheating, obviously. Like if we know exactly the relationship between x and y, like we do here, 2 and 3, well, there's nothing to really fit, right? You already know the model. You already know the relationship. It's no big deal. But what we want to do is make sure we can fit a model and get the same result, right? So what we're going to do is xy is going to x dot reshape minus 1, 1, y dot reshape minus 1, 1. This way, instead of just being a vector of numbers, it'll look kind of like this, just a column of numbers. That's how I prefer it. I don't think it actually matters, but it's fine. And then model is going to be equal to linear regression, right? This is the Scikit-Learn linear regression, which I think internally is just using that this formula, what we just had derived, right? I think it's just using that, so no big deal. So we can do that. And then we can do model.fit x, y, and then we can do model.coef, right? What we want to do is print out the coefficients and the model.intercept. And we can see, just as expected, our coefficient is 3, intercept is 2, because that's how we built the model. Coefficient of 3, intercept is 2. And that's it, right? That's linear regression. Just as a quick review, refresher. I know I spent a little bit more time than I wanted to, but no big deal. Hopefully, if the video is too long, just chunk it up. I think it's important just to kind of have these derivations so you know them. They're helpful to know. But yeah, let's keep rolling. So now we finally start PyTorch, right? So something that I mentioned. So this formulation, right, that we have for this x transpose x inverse. This inversion is actually pretty expensive. There's a ton of research right now that all the computer algorithms people do, and how can we find a super efficient way of doing matrix inverses, especially for large matrices, right? Especially for large matrices. This is a problem if your data set becomes really, really big. And so we need to think of a way of approximating this whole equation here without ever computing the inverse. And to do this, we can use something called gradient descent. Gradient descent is really good at basically approximating what this would have done without ever computing the actual closed form solution. And we'll talk about why this is important in the future in just a little bit. But for now, let's just get a quick idea here. So the principle behind gradient descent is this. So we're going to have one line here and another line right here. And we're going to draw a curve, right? Now, why am I drawing a quadratic? Because our loss function is basically the sum of squared errors, right? So because it's a square, that means it's a quadratic. So we have a quadratic. And we have a, this is our target, right? This is the m that we want, the minimum. And like we said, to find it, we basically take the derivative, set it equal to 0, and solve for w, right? We solve for w. But to solve for w requires this matrix inversion, and we want to avoid that. So instead, what if we do this? What if we say that, okay, I don't know what the best w should be. And if I don't know what it should be, then I should just pick something at random and hope for the best. So let's say we pick here. Let's call this W0. This is my initialization, right? Right here. And so we're going to start with W0. And now what we're going to do is at W0, we're going to compute the derivative, right? This is why AutoGrad is important, because for any function that we provide to PyTorch, it can compute the derivative at a given value, in this case W0. And it'll look something like this, right? The derivative of a line, of a curve, is just really the line tangent to it like this. And so first question is this derivative positive or negative? Well, if you go to the right a little bit, the line goes up. So this is a positive derivative, positive value. What we want to do is descend the curve, right? The correct answer is here. W is down here and we're up here. So we want to move a little bit in this direction. Ooh, let's move back to the regular pencil. We want to move a little bit in this direction, right? That's the idea. So we're going to update W to be W0 minus, and I'll talk about what the learning rate is in just a bit, minus the derivative, right? Minus the derivative at W0. So why does that work? So let's go ahead and erase a little bit of this so it's clear, right? We took the derivative at this point, which we saw as a positive number, right? A positive number. We multiply it by some constant, which we'll talk about in just a bit. And then we subtract from W0 this. So this is actually not W0. This will be W1, right? So now we are here, W1. So we've done a small gradient update on our W1, and now we're here on the curve. Well, let's go ahead and take another derivative, right? Just like we did. So the derivative is, again, a curve. This is a positive value. If we increase a little bit in the x value, or in the w, if we increase w a little bit, we increase our cost a little bit. So again, we'll take a little step in the right direction. So in the direction of gradient descent, right? We want to descend this curve. And now we're here. Right? So now W2 is going to be, and that's why it's a negative. It's negative because we want to descend the curve. So if delta W0 is a positive number, then by subtracting, we're going backwards, right? It's as simple as that. So this will be W1 minus some constant W1, right? So this is an update step again. And then we'll do it again, right? And we'll slowly but surely kind of work our way to here, right? We'll work our way to here. So W, at some point, we will reach W. Now what happens when we reach W, right? What happens if we reach W? Well, this is going to be tangent. So we'll do W is going to be, if we try to do a derivative step, it'll be W minus this, but the derivative at W is just 0. So W is just W, right? It will be stuck there. Now, let's say we tackled it from the other side, right? The weight initialization matters, like which place you randomly start with. So what if we started from the other side? What if we picked here to begin, right? What if this was our starting point? Well, this will be our tangent line, and we're here, right? So this would be our W0 now, in this case, right? This is where we're starting. And so W0 is going to be or W1, sorry, our new W1 is going to be W0 minus some learning rate, which we'll talk about again, times W0. And why is it still minus? Well, what's the sign on this derivative? If we increase in W, our cost goes down, right? Our cost goes down. So if our cost goes down, that means this is a negative derivative. So really, this is going to be W0 minus negative delta W0 for derivative. So this is really W0 plus some learning rate, right? So plus meaning we're going to move in this direction. Again, descending the cost curve, right? So this is the big idea behind gradient descent. Now let's talk a little bit more about the mechanism and how this happens, right? So first of all, we need to talk about this learning rate, right? This thing that I keep mentioning. What is the learning rate? The learning rate kind of determines how optimal our, whatever, I'll just leave that there, it doesn't matter. How optimal or how fine-grained our steps are. So let's erase some of this stuff. There we go. Okay. So for example, this is a constant we have to pick. If this is a small number, right, a very small number, that means we have to do, we'll kind of start here, and then we'll move back a little, 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 over, kind of over and over again, right? So we'll be taking lots and lots of little steps kind of down the curve. The perk of a small learning rate is you will eventually reach your minimum, so no big deal there. But it will take lots and lots of compute, lots and lots of these gradient steps to actually make it there, which makes it kind of expensive and unnecessary. Like there's no need to compute so many gradient steps. On the other hand, what if our learning rate is large, right? Well, okay, so let's say this is my starting point. If my learning rate is large, I might start from here, right? So right here. And then when I do the gradient step, instead of stepping a little bit, I might totally overshoot and jump to here. This will be my W1, because we're just doing W0 minus the gradient times the learning rate, right? If my learning rate is small, you only move a little bit. And if your learning rate is large, you'll move a lot. And we'll just jump over here now. And then when I compute the gradient again, I might jump back and I'll kind of jump to here. And then I might jump to here, and then I might jump to here, and then here, and then here. Like the step is too large. The step size is too large. So picking the learning rate is an important aspect of training neural networks, because if it's too small, it'll take too long. But if it's too large, it will never converge. You'll kind of just be jumping around your cost curve a bunch. Now, mean squared error is somewhat simple. Because I only talked about one parameter here, right? Typically, we're optimizing multiple parameters at the same time. And so your cost curve will actually be a very complicated two-dimensional space that'll kind of be on like a, we have maybe a, let's actually do lines to make it clear. So we'll have this line here, we'll have this line here, and we'll have another one right here. Right, we'll have the cost value. So if we had, let's say, just two parameters, right, W1 and W2, so cost, and we have to optimize W1 and W2, right? That's our goal. Well, this can be a more complicated space, right? This can be a more complicated two-dimensional space for our model to have to optimize on. If we have 5 parameters, then I can't even visualize it. And for big language models that have billions or hundreds of billions of parameters, you can imagine how complicated this space could be. And this, typically, we fall into an issue called local optimums or local minimums. And what does that look like? Well, you've probably seen this in calculus. Instead of just a nice curve, right, quadratic, this only has one minimum. We could end up with something like this. Right, let's say this was our cost curve. Well, let's try gradient descent, right? And actually, let's make this a little bit clearer to give incentive. Right, just like that. So let's say we do gradient descent, right? Well, we randomly pick a number. Let's start here. And we'll take little steps in the right direction, but at some point we're going to be stuck here. We're going to be stuck here because if the model tries to go upwards, the gradient will push it back down. If the model tries to go this way, it'll push it back down. And so we'll be stuck here and we'll never make it to the local minimum, right? Because we don't actually know where the local minimum is. We're hoping we can optimize and get to that point. And so this is why we also have momentum-based optimizers like Atom and stuff, which I won't be going into too much detail right now, but this is a problem that we have, right? And there's all sorts of like issues called like saddle points and other things that typical SGD, so everything we've been talking up till now is SGD, stochastic gradient descent, can't really deal with all that well. And so there's another variant of SGD with momentum, right? With the momentum term included. On the other hand, if we randomly initialized and we happen to start here, well, we'll descend the cost curve to the global minimum, which is great. So this shows two things. First of all, when we optimize, we are not necessarily getting to the local minimum. That's not guaranteed, typically. And the second thing is random initialization matters, right? How we initialize the model can have an effect on the performance of the model. And there's actually a lot of research on the different types of initialization strategies you can take. So let's go ahead and give this a try now. So again, the big idea here is instead of just doing this messy matrix inversion to compute what W should be, we'll start W randomly, and then we'll take the derivative and take a little step. Take a derivative, take a little step. Take the derivative, little step, over and over again until we've hopefully reached a local minimum, or a global minimum in this case. So that's all this figure was showing. So let's go ahead and kind of set this up. This will give you an idea. So let's just throw a seed in here. It's fine. Okay. So how do we set up How do we set up a model in PyTorch? So this will be the simplest model you will see in PyTorch. We're going to do class SGD regressor. Right? This is the name of the model that I want to give it. And then after I compute the SGD, after I set this up, I need to inherit nn.module. So nn.module in PyTorch basically contains all the stuff PyTorch has, all the different layers, all the different options, everything we can think of, everything we would really care about in our model. So we're going to go ahead and inherit it, and that will give it to us. And so then we can do def init, self, and then every class has an init, so we'll put a pass in there, and every PyTorch class needs a forward. Self x. So what are the differences here? So the init is where we initialize the class, and it's where we're going to define the pieces of the model. Right? So where we're going to define all the things this model is going to have. The forward function is the logic of taking some data x and giving it to the model. How do we actually pass it through those pieces? So let's start with the beginning. So we're going to do, first we need to do a super.init. So super.init is basically initializing the inherited class. You don't have to think about it too much. Just make sure you always include it here and you're good to go. If you don't know a lot about class inheritance and all that, it's no big deal. This is it in terms of knowing classes. That's all you need to know. Next, we're going to do self.fc1 is equal to nn.linear11. Okay, so let's break this down real quick. First, nn.linear is a linear layer in PyTorch that takes input of 1 and output of 1, right? So it takes in one input and outputs one output. So in the case of y equals mx plus b, we have one input value x and one input value y. If we had done it differently, if we had w0 plus w1 times x1 plus w2 times x times x2, right? In this case, we have two inputs, x1 and x2, and one output for y. So this would have been 2, 1 in that case. But in our case, it's just 1, 1 because we're doing a simple regression of this problem. We have one input, one output. Good. So this is our linear layer, and that's it. So if we do model is equal to SGD regressor, right, and print out the model, we can see this model is a single FC1 layer that's linear with one input feature, one output feature, and a bias. So I've been calling it intercept, but in PyTorch, the intercept is called a bias. So we can actually probe this a little bit, .fc1. Actually, we'll probe it a little bit later. Let's set up the forward function first. What we need is the logic of passing data x into our y. So in the case, so if we look at x right now, x.shape, it's 20 by 1, right? That's the shape of this data. So this shape here is really batch by 1. Actually, let's not do batch right now. It's n by 1, which means we have n samples, and each sample has one input feature, 20 by 1. And so that's what this model wants. It wants n by, so if this was n by 2, like we had 20 samples and each sample has 2 features, then this should have been 2. If this was n by 50, then this would be 50 here, so on and so forth. So this is exactly the shape we need it in. So we can just do y is self.fc1 x, right? We're basically taking the self.fc1 that we created. The self is also here to make sure that we are creating a variable that's available to the entire class, so we can access fc1 in different methods. So self.fc1 here. And we're just going to, pass x in and create y, and then we can return y. And that's it. Now we need to define, so we defined our model, no big deal. Now we need to define a loss function. Loss function is going to be torch.nn.mse loss. You could also define your own loss function. It's totally up to you. And in future implementations, you see we will do that. But for today, when we do simple things like mean squared error, well, just use PyTorch's mean squared error. It doesn't matter. So we have our loss function. We then need to define an optimizer, right? So like I said, we will be using the stochastic gradient descent optimizer. So torch.optim.sgd model.parameters. And then learning rate is equal to 0.01, let's say. Okay, so what's going on here? What we want to optimize is the parameters of the model. So let's quickly take a look at that. We'll look at it a little bit later in some more detail, but we can do model.parameters. Creates a generator, right? So we can undo it and just do list. So this is a parameter containing this tensor and a parameter containing this tensor, right? These are my two parameters, the weight and the bias. Now, I don't know which is which, so we can actually look at the named parameters in just a bit, but basically we're giving the model these two parameters to optimize. And notice all these parameters have requires grad set to true because these are learnable parameters. We need to compute the gradients of them so we can actually update them, right? So there we go. So, and we have to pick some learning rate. This is an easy example, so we're going to do 0.01. But a typical learning rate for training transformers might be like, 0.00005 or something like that. So either way, this should give you an idea of the optimizer. So we have a model, we have a loss function, we have an optimizer, and then we have to do steps, or in what we typically call it is epochs. So what we have here is 5,000 epochs. We'll talk later about what these epochs are in some more detail, but basically you can imagine as iterations of the data. So we're going to take our data, we're going to give it to the model, compute the loss, update it, and then do it again, and do it again, and do it again, over and over again, 5,000 times. I think 5,000 is overkill for this problem, but it's whatever. So remember, X right now is a NumPy array, because that's what Scikit-Learn wanted when we trained the model above. What we need to do is convert it to a tensor. So X train is going to be torch.tensor X. Y train is torch.tensor Y. So X train looks like this. Now, we don't need it to be float 64. Float 32 is more than sufficient, as all the models also defined in float 32 precision. So we can do d type is equal to torch.float 32. Float 32, and just repeat that on the second one as well. Right, so we have float 32 precision on our data. We'll talk about mixed precision stuff later, like float 16, bfloat 16, all that stuff. But for now, this is fine. Float 32 is the default for most neural networks. Great. So now, just like I said, we can do for name param in model.named parameters. So in model.parameters just returns the parameters. Named parameters will return both of them. We can print out the name and the param. So it tells us that the fc1.weight, this is the m in y equals mx plus b, is this. That's what it randomly picked. And fc1.bias, which is our b, or the intercept, is this, right? These are my randomly initialized weights and intercepts. So all we need to do now is train our model. So we can do for epoch in range epoch, so we're going to do it 5,000 times. Ypred is equal to model x train. So one cool thing about PyTorch is we can do either model.forward, right? We can call the method of this class forward, but if you just do model xtrain, it will do it by default, because in PyTorch there's actually like a call inside the class that will automatically do it for you. It doesn't matter so much, but this is the idea. So we have ypred. Let's print it out. So for each of my x values, for each of my x values, so let's also print out for each of my x values, 0 through this, we've predicted this. This is my predicted y, right? Predicted y. Okay. Now that we have our predicted y, it's the next step. We need to compute, well, these are my predictions, but how wrong am I, right? What is my loss? So loss is going to be the loss function, and it's going to be between ypred and y train, right? This is how wrong I am. And if we look at our loss, we can see my mean squared error is 557, right? So a large mean squared error loss. And notice it has a MSE loss backward here as well for the method, right? So there we go. That's my mean squared error loss. Now for the important part, right? Let's first do loss.backward, right? Loss.backward, right? Just like we did dot backwards before, it will compute the gradient of everything with respect to the loss function. So if we do print model.fc1, right? That's the layer, dot weight or bias, either one. And then we do dot grad. This is the gradient. This is the derivative with respect to the loss function. If we don't have this, so let's redefine from the top, and you'll see why in just a bit. When we don't have it, it says none, right? By default, the gradient is none. And so we need to compute the backward to actually have a gradient. You can see the number's different because every time I initialize these, everything will change because it's randomly initialized anyway. So there we go. Now we can do optimizer.step. This optimizer.step is just what we did here. It's going to do one of these steps of optimization where it's just going to multiply the gradient by the learning rate we picked and then just subtract it from our original weight. So in this case, our gradient was minus 215. Our weight is minus 0.211. So the new one should basically be minus 0.211 minus our learning rate 0.1 times this gradient minus 215, right? So that's basically the setup there. So we have that now. That's loss.backward, optimizer.step. Now, one thing to keep in mind is this is our update, right? We've updated the model, and so we're good to go. And then we rinse and repeat, right? We're gonna again, okay, fine. We have some updated weights. So now, what is the new predictions? What is my new loss? Again, backward step. What is my new predictions? What is my new loss? Compute gradients, update. And we just repeat this over and over again. The problem we have here is that after we do the step, we need to make sure that our gradients are reset to 0, right? We need to reset our gradients to 0. PyTorch by default will accumulate the gradients. So if we do this over and over again, it'll keep adding the gradients to this over and over again, accumulate them, and that's not something we need to do. There are some cases where you do need to do that. When we do like RNNs and stuff, PyTorch needs that accumulation mechanism to do gradients across time, and we'll get into all that later. That's fine. But for now, that's completely unnecessary. So we just need to do a optimizer.0 grad. So now our gradients are now zeroed out. It's zeroed out. So if we do print again model.fc1.weight.grad, it's back to none, even though we compute the gradient. Then we'll just do that over and over again. So now we have this. What we can do now is just let this run real quick. so it shouldn't take very long. And then we can just take a look at our parameters. Notice we started at this and this, but after training, we're at 3 and 2, which is exactly what we expected, right? We saw, I set ahead of time, the slope should be 3, the intercept should be 2. So the model is optimized to slope of 3, intercept of 2, which is exactly what Scikit-Learn gave us. So this should give you an idea, right? This is the easiest form of a neural network we can do with one input, one output. We do some task, some regression task here. We use some optimizer, pass our data through many times, and we are golden. And that's it. Okay, good. So now we move on to the next step, right? Neural networks are good at doing regression. Neural networks are also really good at doing classification, right? So now we need to move on to classification. So I'm hoping you've seen logistic regression a little bit before, but let us, just like I did for linear regression, I'm going to rederive it and show you where this fancy binary cross entropy loss comes from. So it's kind of clear to you what's exactly going on here. So let's go back to here. We are now going to do logistic regression, which is actually a lie. It's not actually a regression task. It is a classification task. I don't know who names these things, but it's fine. Logistic regression. So let's set up the problem here. What is logistic regression? What we have is some input, x, and x can be anything on the real line, right? So that's fine. But y is either 0 or 1, or it's one of the classes or the other class, right? It can be one or the other. So this is A for classification, right? This is used for classification. Okay, good. So let's set this up real quick. So a typical place you would see this would be something like this. So let's draw an axis right here. And let's pretend that, okay, so this is 0. Turn this off, and let's actually make this orange. This is 0. And this is 1. Right? And so our goal is, what we need to do is say, let's pretend all these values, for these values of x, right, it's 0. And for these values of y, or for these values of x, it's 1. Right? So for these values of x, we predicted 0. For these values of x, we predict it's 1. Or we don't predict, but that's what the data is, right? That's our data. And so in linear regression, if we try to train a model on this using simple linear regression, you would just end up with something like this, right? You'd end up with maybe something that looks like this. Oh, something like this. This isn't very helpful to us, to be completely honest. Like, what are we exactly supposed to do with this? This line doesn't really represent anything, and it's kind of, it just isn't helpful, right? This isn't helpful for us. So logistic regression reformats the problem. It rewrites it in a different way. Instead of asking like what y is, what we want really is, what's the probability? What's the probability of y given x? Right? This is the new question we're asking. So we need to somehow represent this as a probability, right? That's step 1. So I'm going to skip ahead to the end a little bit and kind of set it up. Our function, our model, is going to be, let's say, theta transpose x, or we can stick to w, but yeah, let's do w transpose x, right? Which we, where we saw before, right, this is just going to be our w1 x1 plus w2 x2 plus I think I wrote it as xw in the last one, but it's the same thing. It's just the dot product between two vectors, so it doesn't really make a difference. So there you go. Oh, and then plus w0, of course, right? Our intercept term. So that's our setup for this. But this thing will only produce, something on the real line, right? Some value r. But what we want is a probability, not something on the real line. Right? So first of all, what's the range of a probability? Probabilities can be any number between 0 and 1. right? 0% to 100% probability. It's likelihood. So we need to have a function that takes in the real line, right? We need a function, right? That takes in the real line and maps it to 0, 1, right? Maps it to 0, 1. That's the end. That's the important part here. And there's actually a variety of functions that can do this. But the one logistic regression uses is called the sigmoid function. Sigmoid function. So the sigmoid of z is equal to 1 over 1 plus e to the negative z. This is our sigmoid function. So what does a sigmoid function look like? It looks kind of like this. So we'll have this, we'll have this. Actually, we don't need all that space underneath. We can just do this, this. Let's say this is 0 0.5. This is 1. And so the sigmoid function will look something like this. It's going to start, let's do red. It's going to start here at 0 and then slowly increase to 0 0.5 and then taper off to 1. So this means any value at infinity going closer and closer to infinity will just be 1. And any value going closer and closer to negative infinity will be 0. And if you're 0, then it's just 0 0.5, right in the middle. So this is our sigmoid function. And so logistic regression, what it's really doing is attempting to fit a sigmoid function so we get the likelihood, the probability of something to happen. So in this case, the sigmoid function might look, it's going to look terrible, but it's fine. It might look something like this, right? And it'll kind of increase and go here, right? And so this sigmoid function, if our probability is greater than 0 0.5, then it must be 1. And if our probability is less than 0 0.5, then it must be 0. So basically in this sigmoid function, if this is our 0 0.5, right, that means anything before this point, anything before will be predicted as 0. And anything after will be predicted as 1. Which means we've actually misclassified these two with this specific sigmoid function, but I just drew it poorly, right? So it's fine, but you get the idea. So our goal now is not to fit a regression, but to fit the sigmoid function with some parameters. So now the setup is, right? This is the setup for logistic regression. Logistic regression has 2 steps. We have first a linear function, which I'm going to call W transpose X. So f of X is equal to W transpose X. Actually, what did I call it here? Yeah, that's fine. Yeah, okay. Yeah, actually, let's rewrite it slightly better. The logistic regression is trying to model the probability of y equals 1 given x, right? That's our goal. What's the probability of y equals 1 given x? And this is going to be, the probability comes from the sigmoid of z, right? Sigmoid of z creates this probability, where z is equal to w0 plus all of the w1 or wi xi for I equals 1 to the m features, right? So the sigmoid of this provides us the probability. Later on, we'll learn in neural networks, we call this an activation function, right? We'll see in just a bit that neural networks are really just a stack of local linear and then projections to with nonlinear functions. And so that'll hopefully make sense in a bit. But for now, we have a linear function, a linear computation, which z is part of the real line, can be anything. And then the sigmoid of it compresses it to a 0, 1 space. Great. So now that we have that, let us set up the problem a little bit more and then go through the derivation, because I think this is also just as important of a derivation just to have, even though it'll make the video longer than I wanted it to be, but that is totally okay. Just chunk it up and watch it in pieces and you'll be fine. So what we're going to do first is the probability of, let's rewrite this as, instead of just the probability of y equals 1 is x, we can write this as the probability of y equals 1 given x equals x is equal to the sigmoid of theta transpose x, right? That's what we, or not theta, but I've been using w, so w transpose x. The probability of y equals 0 given x equals x, on the other hand, is just 1 minus the same thing, w transpose x, because probabilities have to add up to 1, right? 0 and 1 are my two possibilities, so these two things must add up to 1, so whatever one thing is, the other one must be 1 minus the other thing, right? So these two sum to 1, right? No big deal there. And so let's go ahead and write out our likelihood function. So if you haven't heard of what a likelihood function is our goal is find w that maximizes the likelihood, right? The likelihood of this function. The likelihood is effectively just the probability of the data, the probability or the likelihood of the data. And hopefully this will make sense in just a second. So let's set up one of these probabilities first, and then we'll see what the likelihood function looks like. So the probability of y equals any y given x equals any x is equal to the sigmoid theta, or I keep doing theta, it's really w transpose x to the power y, and then and then times 1 minus sigmoid w transpose x to the power 1 minus y. Well, why does this work? If y equals 0, right? If y equals 0, well, that means this whole thing to the power 0 is just 1, and 1 minus 0 is 1, so I'm just left with this term. So then I'm just left with 1 minus sigmoid w transpose x. If y equals 1, then that will give me just sigmoid w transpose x, right? Because this will be to the power 1, so this will stay, and 1 minus 1 is 0, so this will disappear. So that's just putting these two probabilities together in a single form, and that's it. So the likelihood of the data can then be written as the likelihood of w is going to be the product of I equals 1 to n for the n samples in our data, probability of y equals yi given x equals xi. Right, so what are we doing here? Basically, we're going to loop through all of the samples, compute the probability of each sample given the w, the current w that we have, right? Given the current w. And we'll loop through all the probabilities, multiply them, and then see what the overall product is. And our goal is to optimize w so we can maximize, right? Maximize likelihood. Right? Our goal is to maximize likelihood. We want to maximize this term. I guess I can do this part right now, but it doesn't really matter all that much, but let's just talk about it real quick. Neural networks, right? Neural networks, actually, no, I'll leave it for the end. It's fine. But basically the idea is that neural networks don't actually maximize things, they minimize things, and we'll kind of include that at the very end. That's fine. Let's just keep going with this so it sticks to kind of the default derivation you'll probably see in textbooks and stuff. So that's fine. So we have the likelihood of this. So let's just go ahead and plug in our form, right? So this is going to be the product of I equals 1 to n. And the probability of this is just going to be the sigmoid of w transpose xi, right? The corresponding I times yi, and then 1 minus the sigmoid of w transpose xi times 1 minus yi. Right? So this is my likelihood function of for a specific w, right? For a specific w, and our goal is to optimize w to maximize this likelihood. Well, how do we maximize likelihood? We kind of have to take the derivative, right? Just like before, we're going to take the derivative and set it equal to 0 and see what happens. Except one thing. If I try to do, what I want is d likelihood of w divided by dw. This would be a really big pain to take the derivative of, because there's like product rules and exponents, and then there's another product, and it's just a huge mess, right? This would be this would be very annoying to take the derivative of. Luckily for us, we can use something called the log likelihood. So if you know log, right, log functions is monotonic, right? So in the space that we care about from 0 to 1, if our probability is increasing, then the log of the probability is also increasing. So we can actually find the log likelihood instead. So we can take the log of our function, log likelihood of theta. And so what's this going to be? Well, here basically the idea is the only two principles we have is the log of AB is log A plus log B. That's step 1. And log of A squared is just 2 log A, right? These are the two principles we'll use. So we have a product here. This product, because of log, will now become a sum. So that's one huge hassle gone. So I from 1 to n. And this product here becomes log of this times the log of this. So it'll be the log of this whole term. So it's log of sigmoid W transpose Xi. And this W transpose Xi is to the power Yi. But like we saw here, the exponent can just come out in front. So really, this is just Yi log of this plus 1 minus Yi, for the same reason, 1 minus sigmoid W transpose Xi. Right? So this is my log likelihood function, and this is basically your binary cross entropy. Right? This is what PyTorch calls the binary cross entropy, except again, like I mentioned before, we want to maximize the log function, or we want to minimize the negative log function, right? Negative log. And so that negative is what binary cross entropy includes. We'll just toss it in at the end, so that's fine. Good. So we have this log function. Now what we want to do is go ahead and take the derivative, right? We can do d log L of theta divided by, I keep writing theta. I really need to not do that. There's anything else? No, okay, let's fix that. Sorry, these theta should be W. I just used to theta, but I want to keep the notation as consistent as I can, just so it's clear. There we go. DL dW, and then we're going to do dW with respect to W. So no big deal. Well, how do we take this derivative? Well, there's going to be a chain rule, right? We have a sigmoid function in here, first of all, right? So we're going to have to take the derivative. So if we have y is equal to sigmoid of x, y prime is going to be the sigmoid of this derivative of the sigmoid times the derivative of x, right? That, like, chain rule stuff. So a good thing we can go ahead and do ahead of time is just compute the derivative of the sigmoid, right? So, okay. So our sigmoid of z is 1 over 1 plus e to the negative z, which we can also just rewrite as 1 plus e to the negative z to the power negative 1, right? And so if we do the derivative d dz of this thing, well, that'll be negative 1 plus e to the negative z, negative 2, times, well, the derivative of the stuff inside, well, the 1 doesn't matter. So it's just derivative of e to the negative z, which is e to the negative z, times the derivative of negative z, which is negative 1. And so really this is just 1 plus e to the negative z, or actually let's put it back in the denominator. So it'll be e to the negative z divided by 1 plus e to the negative z squared, right? That's our derivative. Now we could technically leave it here, but there is a interesting property for the derivative sigmoid that we can exploit. So let's go ahead and split this up. We're going to do 1 over 1 plus e to the negative z, right? So this thing here continues here, sorry, times e to the negative z divided by 1 plus e to the negative z, right? So we just took this square term and just split it up like this. No big deal. Now that we have that, we can do a quick little trick. So this is the same as 1 over 1 plus e to the negative z times 1 plus e to the negative z minus 1 over 1 plus e to the negative z, right? Nothing too crazy. We're just adding 1, subtracting 1, so nothing ever changed. And so then we can rewrite this as 1 over 1 plus e to the negative z times 1 plus e to the negative z over 1 plus e to the negative z minus 1 over 1 plus e to the negative z, right? Because it's just a minus b over c, so that's a over c minus b over c, right? So nothing too crazy. Well, this one is obviously 1, right? So these things will cancel, so that'll be 1. So that simplifies our problem a little bit more. So that'll be equal to 1 over 1 plus e to the negative z times 1 minus, and there should be a big thing here as well, 1 minus 1 over 1 plus e to the negative z. And what is 1 over 1 plus e to the negative z? Well, this is just sigmoid of z times 1 minus sigmoid of z. And that's a cool thing about sigmoid functions. It's why sigmoid function was probably one of the reasons it was used, just because it's very convenient to compute the derivative of. So we have basically the derivative of the sigmoid of z is equal to sigmoid of z times 1 minus sigmoid of z, and that's it. We're going to be using this property just for convenience. So now let's go ahead and compute our log probability, right? So that's this, basically the derivative of this whole function up here. So we have d log of our log likelihood times, or the derivative with respect to dwj. So what is wj? So remember, we have, we might have w might be a vector of w0, w1, w2, ... wm, right, for the m features. Well, we need to update each of these individually, which means we need to take the derivative with respect to each w individually, which means we need to do it with respect to some wj, where j is, j is a part of 0 to m, and technically if we're doing this, this should be a partial derivative, right? That's, notation, but whatever. So this is going to be equal to the partial derivative wj j of the function we had from before. So I equals 1 to n yi log sigmoid w transpose x plus 1 minus yi log 1 minus sigmoid w transpose x, right? So this is our function that we want to take the derivative of. Okay, no big deal. The derivative of a sum is the sum of a derivative. So this is equal to the sum I equals 1 to n, right? Just like before. And we can stick our derivatives inside. So this is wj yi log sigmoid w transpose x plus, again, stick them inside, or keep data, wj 1 minus yi log 1 minus sigmoid of w transpose x, just like before, right? So all we did is stick our derivatives inside, no big deal. And so now let's go ahead and take the derivative. So this is going to be the sum I equals 1 to n, and the derivative of this is going to be, well, the derivative yi is just a constant, so it'll be yi, and the derivative of log of x, right? So log of x, the derivative is just 1 over x, right? That's the derivative of log. So the derivative of log of this is just going to be divided by the sigmoid of w transpose x times, now we do chain rule. What's the derivative of sigmoid w transpose x? Well, we know that. It's going to be sigmoid w transpose x times 1 minus sigmoid w transpose x. And then the derivative of W transpose X with respect to Wj will be, and actually I'm missing some indexes here. This should be Xi, right? And this should be Xi. Yeah, let's put these back in, right? Because it's for which sample are we on, right? So Xi, Xi. There you go. And so this should be Xi, Xi. And YouTube, Xi. There we go. Sorry about that. So yeah, so we're doing the derivative, and now we're doing the derivative with respect to Wj. So that'll be Xij. So why is that? First of all, the Xi, I indicates which sample are we on, right? We have n samples, so that's Xi. And really what we have is W1 X1 plus W2 X2 plus ... Wj Xj plus ... W mxm, right? And we also have our w0, right? This is our thing. So the derivative with respect to some wj will be xj, right? It's corresponding j. So xij is our kind of notation for that. No big deal. Now that we have that, we do the same thing for the other one, right? So plus, this will be 1 minus yi divided by 1 minus sigmoid w transpose xi, right? And then what we can do is just multiply by the derivative, right? So the derivative of this, and then we do the derivative of the inside function. Notice we have a negative here now, so we're going to have an extra negative 1 term. So it's going to be times -1 times the derivative of sigmoid is sigmoid w transpose xi, 1 minus sigmoid w transpose xi, right? And then we have, again, the derivative with respect to the inside term, which will again be xij. So this positive and this negative, we'll just make this a negative, so that's no big deal. But notice something here. All of this here and all of this here is the same. So we can just go ahead and take it common, right? We can take it out. So let's go ahead and do that. So this is going to be equal to the sum I equals 1 to n. We'll have yi over sigmoid w transpose xi minus, it's minus again because this -1 and this positive here make a negative, so minus, we'll have 1 minus here, 1 minus yi by 1 minus sigmoid w transpose xi, and all of this will be multiplied by the thing we took out, right, which will be sigmoid w transpose xi, or 1 minus sigmoid w transpose xi times xij. And there we go. That's our kind of big summary of everything that's going on. And we can start to now simplify this down, and you will see what happens. So yeah, I'm not going to skip any steps. Let's just do it. We've already come so far. So this is going to be equal to the sum I equals 1 to n. So if we want to put these together, cross multiply, so that'll be yi times 1 minus sigmoid this thing. So that'll be yi minus yi sigmoid w transpose xi, right? So that's this times this, minus 1 minus yi times this will be sigmoid w transpose xi. And this negative and negative will make a positive. So this will be plus yi sigmoid w transpose xi. And this whole thing will be divided by sigmoid w transpose xi, 1 minus sigmoid w transpose xi. You can start to see some stuff that we saw before return. And let's go ahead and write the rest of it. And this whole thing will be multiplied by, again, sigmoid w transpose xi, 1 minus sigmoid w transpose xi, xij. Yeah, that looks good. Now, luckily for us, this term here and this term here cancel. So, and then this whole term here and all of this here cancels, which makes it very, very simple for us because all we're now left with is our final result. I equals 1 to n yi minus sigmoid w transpose xi times xij. Great. So this is again the d log likelihood of some w dw, right? And our goal is we want to maximize this. We want to maximize this likelihood. Now a problem, right? And this is why gradient descent is so important. What we haven't done, right? We wanted to take this and set it equal to 0, right? Set it equal to 0. If we set this equation equal to 0, there's no way to solve for W, right? No, not that I know, right? So logistic regression, right? Logistic regression, no closed form solution, right? There's no closed form solution because there's no way I can set this equal to 0 and solve and just get a direct answer, which is why we really depend on optimization. We have to take little steps in the right direction. And so what we did, all we did is found the logic for the gradient, right? All this stuff we did is logic for the gradient. So if we want to maximize this, so let's go back to that. If we want to maximize this, that's same as if we want to maximize A, that's the same as minimizing negative A, right? That's same as minimizing negative A. So really what we need to do is minimize the negative log likelihood of W, right? Minimize, and this is basically your binary cross entropy loss, right? If we again scroll back up a little bit and take a look, this whole thing that we took a derivative of, we want to maximize this thing or minimize the negative of this thing. And so that's why it's called binary cross entropy, or that's basically the binary cross entropy loss of PyTorch. And to do this, basically our derivative then becomes just the negative I equals 1 to n yi minus sigmoid w transpose xi xij, right? That this is our derivative of the binary cross entropy loss. Great. So this sets it up. Again, there's this is probably a little overkill on an introductory PyTorch tutorial, but I did want to do a separate video on just these derivations, and I really think it's important to just have them. These basically, the principles we talked about here are super important, but what you just saw is that we took, again, this whole deal here is a linear transformation, right? You're taking x, multiplying it by some w's, adding some intercept term, but then we pass it through a nonlinear function that crushes the kind of the domain that in which our output exists in, which is fine. But now that in neural networks, we typically call this the activation function. And now that we've included an activation function, we no longer have the ability to take the derivative and solve a closed form solution for this problem. And this is exactly why we have to do gradient descent, right? This will have some weird cost function, and we need to basically take little steps in the right direction. So hopefully, right, we can reach some optimal minimum, right? And the only way to do this is by the gradient. Now, the cool thing is all of this fancy gradient manipulations and computations and everything I did, this is just fancy chain rule, right? Over and over and over again. So PyTorch's AutoGrad system will do this for you automatically, right? That's what makes AutoGrad really brilliant, because it looks like fancy math, all of this stuff, but in the end, it's really not. It's just a bunch of addings and multiplyings and dividings, and AutoGrad can take care of any of that for you. So let's go ahead and finally build it. Sorry again that it took so long. It just is important that, at least I think it's important to see some of these derivations, just so you can start tying all these pieces together. So yeah, so here's our binary cross entropy loss, just like I had mentioned, right? The yi times the log probability of yi, and the probability of yi, the probability of 1 minus y, is really just the sigmoid function, right? The sigmoid is what's creating those probabilities. So let's go ahead and create some data. So I'm just going to copy paste this portion in because I don't want to type it and it doesn't really matter But what I've done here is create some dummy data, right? We have a classification data, and this data set, notice the input and output. The input is two numbers, this axis and this axis, like where is it in these two-dimensional axes? And the output is 0, 1, right? Is it a yellow or is it a purple? And that's basically it. And so we can go ahead and actually train a model. So we had, I think I copied this in the wrong place. So let's put you up here. I guess you can't see this, it's a dark mode, but we already drew the sigmoid function and went over all this, so no big deal. And so now let's go ahead and do exactly what we did before. Torch.c, so it's reproducible, and we're going to do class Logistic Regression. Okay, just like before, mn.module def init self super.init, and then we're going to do self.fc1 is nn.linear 2, 1. So why is it 2? Because we have two input values, right? So if we, I guess I didn't show it. Let's just quickly check. X looks like this. If we look x.shape, X has 750 samples. There's 750 samples in X, and each sample has two numbers in it, right? Two values. So that's why it is that's why we have two inputs. It's n by 2. Y, on the other hand, is a bunch of zeros and ones, so dot shape. Now it is one output. And that should make it clear why we have two inputs, one output here. Similarly, our forward self x and y is going to be self.fc1. Actually, let's keep it the same. Z is equal to self.fc1 x. Return z. So our model is equal to logistic regression, right? And our loss function is torch.nn.bce loss, right? This is our binary cross entropy loss, the one that I keep mentioning. Our optimizer is going to be equal to torch.optim.sgd. Again, we want to train model.parameters, and learning rate is 0.01. And epochs equals 5,000, right? This is our setup. Which one am I missing? Parameter should have a parentheses after it. There we go. Now, let's say I'm going to do model. I think I have to do the same thing as before. So x train is torch.tensor x. The type is torch.float 32. Y train is equal to, again, torch.tensor y. D type is equal to torch.float 32. And then we can return, let's just give this a quick example here. So we can do model x train. So these are my predictions. Now, what do you notice about these predictions? They're kind of, they're a bunch of numbers, right? They're just a bunch of numbers. And that's not helpful to us. We want to not predict numbers. We want to predict probabilities, which I mentioned requires the sigmoid function, which we never applied. So now, instead of just returning z, we're going to do y equals torch.sigmoid c. And then we'll return y. Now notice our numbers, right? They're all between 0 and 1, right? So we have a nice probability value. So the sigmoid is basically doing what we had just seen. And so that's our model. Everything's good to go. Now, just like before, we're going to do for epoch in range epochs, right? I spelled that right? Yeah, I did. Okay, good. We're going to do y pred is equal to model x train. And then we're going to do loss is equal to the loss function between y pred and y train. And then just like before, loss dot backward optimizer.step, optimizer.zero grad. What did I spell along? Oh, range. Sorry. There you go. So we've now trained our model. So how do we find out our model's accuracy? So what we can do is ypred, let's call this y final pred, is equal to model x train. Now, one thing just to keep in mind is when we inference, like in this case, right? In this case, we're just inferencing the model. We're not training it, we're inferencing it. So all this stuff, right? All this stuff that PyTorch does, the things we covered at the beginning, right? Creating these computational graphs, it's not really necessary if you're not training. You only need or it's not necessary if you're inferencing. You only need them when you train, right? So if we're not training, then we don't need to make all this stuff. And so we can make, we can wrap this with a torch dot inference mode, right? So this will basically not compute the graph. It'll just provide, it doesn't do anything else. It'll just provide the prediction. So these are my predictions, right? Oh, scroll too far. Scroll back down. There we go. These are my predictions, right? Predictions. So we talked about this, but if our sigmoid function, right, if we take a look at it again, where'd it go? Here. If we're above 0.5, then we're predicting 1. And if we're less than 0.5, then we're predicting 0. So let's do that. If we're greater than 0.5, right? So you can see some are false, some are true, right? Whichever one's greater, whichever one's less. And what we're going to do is just convert it to a .int. Just to keep it simple, right? So we predict zeros for these and ones for the other ones. And we also have our y train, right? These are my true values, and y final pred are my predicted values, right? And convert it to int. So we can just do equal to y train. And this will tell us which samples did we get true, like they're the same, and which ones are not true, they're false, so those are incorrect. We can then sum them up. Or we can do torch.mean. Wait. I missed a, that's fine, let's just. I'm missing a parenthesis somewhere, let's just undo this. Let's undo this real quick. Okay, so there we go, I'm missing this one right here. There we go, and we can convert it to an int. And then we can just take the mean, torch.mean, which will add up all the values and then divide by the number of values. I guess float. There you go. So we have a 96.8% accuracy, right? We got 96.8% of our predictions correct, which is pretty neat, right? We can also go ahead and try to I think it's fine. I think this gets the point across, right? So I think we're good. In the case, did I have an example where I plotted it? I guess not. Okay, that's fine. Yep. All right. Neat. So this should give you an idea of kind of a simple classification task. So we're going to wrap this up by basically going through a MNIST problem, and this is where we're going to explore the rest of PyTorch. So this is really where most of the PyTorch stuff will begin. Sorry again, I just really think it's important to get all of that math down because it does show up all over the place. So what we're going to do now is train a MNIST model, and I'm going to copy paste a little bit of this just so it's easy. So I already downloaded my MNIST dataset to this path. Just provide it any path and it'll automatically download it. So I'm not going to go into this dataset stuff too much right now. The next video will be directly on building datasets and data loaders for PyTorch. So I'm not going to dig into it too much right now, but basically these datasets, contain the data. They contain the data of our stuff. And so if we if we take a quick look at this is the MNIST dataset, and we're providing a transformation because the MNIST dataset, all the images are stored as like PNGs or JPEGs or something like that inside the computer. Not very helpful to have them as that. We want them to be tensors, right? PyTorch tensors, so we can actually work with them. So this, we just provide a transformation that will convert to tensor. Again, we're going to do a huge deep dive in building data sets and data loaders for computer vision and for natural language processing in the next video. So don't worry about this too much right now. But all you need to know about these data sets is they're iterables. They're basically, we can for loop them. So we can do for data in train, and we can print the data. Oh, and let's just break. So you can see the first thing in the data is all these numbers, and we'll see what these numbers are. And the second thing is a class label 5. So really what this is for image label in train, we can print the image, which is this stuff here. All this is my image data. And let's quickly take a look. Dot shape. This image is 1 channel by 28 by 28 pixels. Okay, cool. And the label is 5. Right? So that gives us everything we need. But let's quickly visualize one of these images. So what we're going to do is we're going to do image is equal to image.squeeze, because we don't really, so image.shape. So dot squeeze removes any redundant dimensions. A redundant dimension is a dimension with just 1, right? Like this 1 doesn't really do anything. If this was 3, then we'd actually need it. Like there's information there. But if it's 1, it doesn't really matter. So image.squeeze will just get rid of that 1 and just leave us with the 28 by 28 that's left. No big deal. This is the equivalent of, by the way, like if you had a 1, 2, 3, like a list, and then you wrap it in another list, well, then you've fake added 2 dimensions. We don't really need that, that's double list. So that's just getting rid of it. So we have the image, and then we can just quickly use a, and dot numpy, right? So we want to convert it to a numpy array just so we can, actually, I wonder if we can just plot it directly. Let's see, plt.imshow image. Oh yeah, we can. Okay, so we don't need a numpy array. So as you can see, it is the number 5, right? It's the number 5. And we can do cmap equals gray because imshow doesn't know. So we're just making sure it's a black and white image. And there you go. It is a 5. Nothing too crazy. And we can see the label is 5, right? Nothing too crazy. So there we go. That's basically our data. And let's just throw a counter in there. Counter equals 0. And let's do plt dot title, and let's put the label in there. plt dot show. Right, so it's just like that. And we're going to do counter plus equals 1, and if counter is 10, then break. Just so we can plot out a couple of these. You can see it's 5, a 0, a 4, a 1, 9, 2, whatever it may be. So MNIST is a handwritten image data set. And that's it, right? It's just a handwritten image data set. And our goal is, given this picture of this digit, predict what is it, right? What is the number is the goal. We'll be tackling this in 2 different ways. Today, just a regular kind of stack of linear layers. In a couple videos, we'll be doing convolutions, and it'll kind of make more sense. But for now, let's just go with this. And when we get to convolutions, we'll get there when we get there. So I think I guess I just did it a little bit early on, so it's fine. No big deal. So let's go straight to here. Neural network considerations, right? So couple things we need to talk about when it comes to neural networks. Number 1, the batch size. So everything we've done so far, for example, let's look at this one here. We have an X train and a Y train, that's our data, and we take X train and pass it into the model and get some predictions. And that's great. This is actually ideal, right? We're passing our data to our model, computing the global loss, right? This is the loss of the entire data set. And once we've computed this global loss, we can now, update the model accordingly. Okay, fine. But this is probably not possible. For example, if we look at MNIST, right? We have, let's print out train again. We have 60,000 images. We have 60,000 images, and probably on modern GPUs today, we could actually pass all these in because these are images that are all that big, so it doesn't matter. But let's imagine we have 1 million high resolution images, kind of like the ImageNet dataset, which we'll work with later, right? High resolution images. Well, if we have 1 million high resolution images, there's not enough GPU memory on most computers, except for maybe some of the biggest clusters, where you can pass all of that data into your GPU in one iteration. I hope that makes sense. So our data set is too big to fit inside the GPU or inside the computer. I know we haven't talked too much about GPUs yet. We'll kind of get there in just a little bit to see how GPUs play a role in neural networks. But for now, it's okay. Just assume that there's not enough compute available to just pass millions of images to a model in one go. So because we can't do that, we instead batch it. Batches are basically how many samples do we want to feed at every time. Now, there's a ton of research about what batch size you should use. I haven't followed it all that well. Typically, the idea is fit the largest batch size that will fit inside your memory, inside the compute you have available to you. And so imagine it this way. If you have 1,000 images and your batch size is 100, that means you have 10 batches, right? So if you have 1,000 images, and you have 10 batches, and each batch is equal to 100, n is equal to, let's say, 2,000, right? And batch is 100. That means we have num batches is going to be n divided by batch, right? Which is just going to be equal to 200. Or sorry, 20. We have 20 batches. So this means we're going to, have our data set. We're going to grab a batch of 100, give it to the model, optimizer.step. So let's scroll up again, right? We're going to grab a batch, give it to the model, compute our prediction, compute the loss, optimize our model, rinse and repeat with the next batch, the next batch, the next batch, over and over and over again. So we're optimizing based on batches now. In this case, 20 batches. Once we've completed 20 batches, in this case, right, we've exhausted all 2,000 images, and that is a single epoch, one full iteration through the data. And then we'll basically repeat that, maybe 5 epochs, 10 epochs, some number of epochs of time. But there's some considerations to be made, and we'll get there in a second. The optimizer, how will we descend the cost curve? So we talked a little bit about this. Stochastic gradient descent is kind of great, but it's a little bit optimistic that there's no local minimum in your optimization curve. So if there isn't, we need some type of momentum-based optimizer, and Atom seems to be the most robust for these types of tasks and is basically used in most language models and stuff like that now, so we're just going to use Atom for now. But obviously, different optimizers might play well with different types of problems, so you kind of have to test and see what works well. You then have a loss function. How do we compute error? Again, this is highly dependent on the problem, and as we start exploring more complex architectures, like maybe wave-to-vec for speech processing and other stuff, you'll see that the loss function does depend on the problem, but there are some kind of defaults you can go with. If you're doing a classification task, then you're good with using binary cross-entropy if it's a binary problem like 0, 1, or just regular categorical cross-entropy for multi-class. So in our case, in MNIST, we have handwritten digits from 0 to 9. So there's 10 classes, right? 0, 1, 2, 3, all the way up to 9. So we can use regular categorical cross-entropy, which is just an extension of binary cross-entropy to the multi-class task. So it's just binary cross-entropy just for multiple classes rather than just 2. And so we can use that in this case. Okay, good. So we have our loss function. We have to pick that based on the problem. Epoch, so how many full iterations do we want to do through the data? And this leads to something called overfitting and underfitting, which we'll look at in just a second. And the learning rate. How quickly do we want to learn? If your learning rate is too high, you'll have unstable training, but if it's too low, then it'll take more time than necessary. So kind of playing with that is also an important thing to do. So good. Now, overfitting and underfitting. So let's kind of take a look at this. The analogy I always use for overfitting and underfitting is this. Let's pretend you are studying for an exam, right? You're studying for a math exam. So there's kind of 2 ways to study for a math exam. The first way is look at all the previous exams, look at the previous homework questions, the previous quiz questions, and memorize them, right? Memorize exactly the steps you did to solve all the different types of problems. This is fine. And so when you go to take your exam, right, when you go to take an exam, if all the exam problems are exactly like the practice problems that you've looked at, then you're good to go, right? You've already memorized how to do it, so you just do it again. But what if your teacher or your professor gives you a trick problem, right? Gives you a trick problem, something you've never seen before, but is something that you should be able to do with the knowledge you have. Well, if you don't understand the math, then you couldn't solve the problem. And so this is how you can understand overfitting and underfitting. First of all, underfitting is where you just did not study for your exam at all, right? Like the model you have here is not fitting your data at all. You just don't do well. So you just didn't study enough. So that's underfitting. Overfitting is you've effectively just memorized the data. You've memorized the exam problem. So you know exactly how to solve these exam problems. But if I give you a brand new exam problem that's different, you may not be able to answer that question. And so a balanced one is generalizing your data. What you don't want is to perfectly carve out your data, but rather kind of get the general trend of your data. Even if that means there may be some error, it's better to have a general idea of kind of how your data is, or a general idea of how to solve these math problems, rather than exactly memorizing them. So there you go. This is it. And we'll see an example of overfitting a little bit later because it's very easy to overfit on the MNIST dataset. So there we go. Next, the activation function, right? The activation function, there, like we talked about in neural networks, we need to include some nonlinearity. Sigmoid does, or the logistic regression function does this by incorporating a sigmoid function. But in neural networks, when we have deeper neural networks, and that'll make sense in a bit too, when we have these deeper neural networks, we can have lots of activation functions, right? So let's quickly look at an example of that right here. I'm not going to derive it because there's no way to really hand do any of this. We'll do a short hand done example when we go to implement AutoGrad another day, but today we'll keep it simple. So what we're going to do is our neural network, right? This is our neural network, right? Basically we're going to have some x and we're going to have some y. And so we're going to first have a function f of x, which is going to be w transpose x, right? So we're going to multiply x by some weights. So this is a linear operation, right? Just multiplying and adding is a linear projection, linear operation. Then we're going to create a g of x, which is going to be the, let's say, the sigmoid of f of x. Why sigmoid? I don't know. It's just an arbitrary activation function. You can pick any one of them. And so this is going to be a non-linear operation, right? Sigmoid is a nonlinear function that looks kind of like this, right? 0.5. So then h of x will be, let's say, w2. So this is w1. Let's say let's put the 1 down below. It'll be another set of weights, right? w2 transpose g of x, right? So this is another linear operation. And then we can do let's see, I of x is equal to the sigmoid of h of x. This is, again, a nonlinear operation. So neural networks are basically a stack of operations that typically, oscillate between linear, nonlinear, dot, dot, dot. And the more of these you have, the deeper the network, right? That's why it's called deep learning. This makes it deeper the network. Right? The more of this you have, the deeper your network, and that's the main idea. And so let's go back here. So we talked a little about overfitting and underfitting. Epochs is one way of causing overfitting. This is if you see your exam problems too many times because you've gone through them so many times, then you'll immediately have memorized the data, right? Another way to overfit and underfit is if your model is not complicated enough or too complicated. Like if you have a very complex model with lots of learnable parameters and the model can kind of do all sorts of stuff and kind of learn all sorts of things, then there's a chance that it'll just immediately memorize the data, which isn't good. But if your model's too simple, like in this case, what we want is a curve, right? To separate these classes, we want a curve. But if you force your model to be a straight line, then this will always underfit because a line can never model something that requires a curve. So this is a overly simple model. This is a overly complex model. You can see that it's capable of wiggling around and being super flexible and perfectly carving out your data. So this would be a overly complicated model. And so that's another example of how overfitting and underfitting can happen. And so yeah, we talked about this. We talked about gradient descent. This is just another way of looking at gradient descent. So ideally, right, we would just pass in our whole data at one time, but that typically is too expensive. Mini batch is not good either. So mini batch is basically passing in one sample at a time, optimizing on one sample at a time. So these are your two extremes, right? You either pass in all your data in at once, or you pass in one sample at once. And passing all of them in is not possible. And passing one at a time in is very noisy, right? You'll have a very noisy cost curve, and the optimization won't be very well. What you want to do is have a large enough batch size so when you take the average gradient across that batch, it's a good approximation of what that gradient should have been for the entire data set, right? This is why we take averages. It's to kind of smooth out all of those all the noise there. So that's why we're going to be using batch gradient descent and so on and so forth. So we'll get like nice smooth optimization curves. Okay, so let's define some of these starting points. We're going to use a batch size is equal to 128. So this is going to be a, so this is basically in our MNIST, we're going to be using 128 images at a time, and that's it. Our loss is going to be nn.cross entropy loss. So quickly, just so you know, right, our binary cross entropy, right? Binary cross entropy was negative some yi log probability of yi plus yi or 1 minus yi log 1 minus probability of yi, right? That's our binary cross entropy. Cross entropy is just a simplification of this. We're going to do negative sum probability times the log of the probability, and that's it, right? So this is just simplification. This is basically the same thing as this, right? You just summed up for the binary task, but yeah, this is fine. So this is basically our cross entropy loss. We'll dig into this a little bit more in just a bit, but for now, let's just keep going and try to define some of this stuff. So we have our cross entropy loss. Our learning rate is equal to 0. Let's say I picked 0.008, so that's what we're going to go with, whatever. And epochs equals 5. We're going to train for 5 epochs. So there we go. Okay, so let me open up this and just keep that for now. All right, yep, good. So yeah, let's just hold on to that. We'll do that later. All right, so now we're going to create our data loader. So, well, again, we're going to go into a lot of detail about this later, about what data sets and data loaders are in a future video, but at a high level, all you need to know is a data set is the logic to go into your hard drive and grab one image, right? So this is going to go in and grab one of the image and its corresponding label in this case. A data loader, on the other hand, is the logic that wraps the data set and goes in and grabs batches of images, like 128 of them at a time. In this case, we're going to do train set is going to be torch.utils.data.data.loader, right? And it's going to be on train. So we called our MNIST training data as train. Batch size equals batch size, 128 that we picked earlier. And shuffle equals true. So when we're training on data, we want to make sure it's like a random shuffle every time, so it gets different combinations of batches every time. So we're going to shuffle it up. And then we're going to do test set is equal to, it's going to be exactly the same thing, but it's going to be test here. Now, one thing to keep in mind is sometimes your training, like the data loader, the whole process of going into your hard drive and grabbing stuff, it can be expensive, right? It can actually be expensive. So PyTorch is really neat because instead of grabbing them sequentially, you can include num workers equals, I don't know, 16. So you'll have 16 threads kind of doing all this stuff in parallel, and it's great, but we don't really need to worry about this now because MNIST is a very simple data set to grab stuff from. And so if we do for images, labels in train set, we can print images dot shape and print the labels and break. So you can see my images are, we have 128 images. Each image has one channel because it's a grayscale image, and each channel is a 28 by 28 image. And that's it, right? Nothing too crazy. And here's our labels, right? We have different labels, right? This first image is a 1, then an 8, then a 7, and so on and so forth. And every time you do it, it'll grab, different samples because it's random, right? It is random. So now what we need to do is build a dense network. And this is a typical, this is how your neural networks typically look. You have some inputs. These lines here are basically the weight matrices, weight matrices, weight matrices, right? Over and over again. So multiple projections over and over again. So before we do anything, though, we need to think about the input and the output of our model. So we'll come back to Softmax in just a second, but let's do this first. We're going to do class fcnet nn.module, and we're going to do def init self, just like before, super dot init, just like before, and then we're going to have it def forward self x. Right, we're going to do this for now. And so question number 1, we're going to do a linear layer here. Self dot fc1 is equal to nn dot linear. But the first question is, what is the input? What exactly is the input to this model? Well, how many pixels do we have? So let's take a look here. So each sample, each image, right? So we have 128 images. Each image is 1 by 28 by 28, right? That's our thing. So we can actually take this and flatten it. So an example of this would be torch.randn, let's say 4 by 4, right? So this is our image, a 4 by 4 image. So we can print A, and then we can print A dot flatten. So this was my 4 by 4. Actually, let's make it a little bit smaller. So let's do 3 by 3. Maybe it'll fit in the line then. 2 by 2 line. This is my super tiny 2 by 2 image, right? And we can take our 2 by 2 image and represent it as a single vector of all the features. And each of these basically represent the pixel values of our image, right? So we can take our 1 by 28 by 28 and flatten it to become a single vector. And if we look at 28 times 28, that gives us 784. So our input here will be 28 times 28, or 784. And our output is what? What is our output? Well, in this case, our output is 10. Why is it 10? Because we have 10 possible outputs in our model. And so this is the important thing to keep in mind. BCE loss, right? Binary cross entropy expects one output where greater than 0.5 is 1, and less than 0.5 is 0, right? Those are my class labels. Cross entropy loss expects two outputs where the first output is the probability of 1, and the second output is the prob of 0, or vice versa, it doesn't matter. So let's kind of draw this out. So we can either, right, so we'll have some neural network, and it's going to have some inputs, right? Let's say there's these inputs, and then either we have one output, and this can go to binary cross entropy loss. So no big deal, where greater than 0.5 is 1, and less than 0.5 is 0. Or we could have, if we want to use cross entropy loss for a binary problem, then we can have two outputs, where this is the probability of 0, and this is the probability of 1. In the case of MNIST, right, we're going to have 10 outputs, 0, 2, 3, 10. So this is the probability the digit is 0, probability the digit is 1, probability the digit is 9, right, 0 through 9. So we have 10 outputs. But here's the problem. Our neural network, remember this, our neural network can output any kind of number, right? Any number can come out the other end. And same with the logistic, when we did logistic regression, any number comes out the other end, but we had a function that mapped the real space, right, to some 0, 1. Now what we have, right, our output, these are the raw outputs are typically called logits. They're going to be some numbers, right? Let's say, I don't know, 01, 02, 03, actually let's start at 0. So 00, 01, 02, 09, right? These are going to be my 10 outputs. I need to convert this to a probability vector, right? So it'll be probability 0, probability 1, probability 9, such that, right, first of all, the sum of our probability vector, right, is equal to 1. So the sum of this vector is 1, and the max, right, the max value is basically our prediction, right? We predict whatever is the most likely output. And the way we can do this is via the Softmax equation. So what is Softmax? So if we have, so let's say our output is output 0, output 1, output 2, right? Our Softmax equation is exp xi divided by sum exp xj from j equals 1 to the m features. In this case, it's 3. So this means O0 will become exp O0 divided by exp O0 plus exp O1 plus exp O2. The next one, O1, will be exp O1 divided by the same denominator. And the third one will be exp O2 divided by the same denominator, right? So it's the same denominator over and over again. So if we have the same denominator, first of all, if we sum all this together, if we add it all together, those be it's the same denominator, so it'll just be the same denominator. Then it'll be exp O0, O1, O2, and so it'll be 1 over 1, so that'll be 1. So the sum of these things are 1, so it matches the probability, and whichever one of these things are the largest is the one that we will pick as our prediction, right? So hopefully that makes sense. So we need to do this softmax conversion of our data, of our output of the neural network. So let's go ahead and do that. So what we're going to do is I'm going to get rid of you. We have one layer, it's going to go from 28 to 28 down to 10. And then we're going to do, first, so this is why I meant we should always create some random data. So it's called rand, it's torch.randn. We know our data is in the shape of 128 by 1 by 28 by 28. It's going to create a random tensor. And we're going to do model is equal to fcnet, right? And we're going to do model rand. We're going to pass our data in. So if we print here x.shape, we can see this is our data. What we want to do is x equals x.flatten. Now this flatten will flatten everything, which isn't good. We want to keep the 128, but we want to flatten everything else. I think if we do flatten 1, it'll basically start from the first dimension. So we can basically, it'll skip the first one and keep going from the other. Or we could have done x dot, we could also do it this way. We can do batch size is equal to x dot shape 0, right? That's our batch size. So this is 128. And we can do x dot reshape batch size by everything else. So both of these are valid ways of doing it, however you want. And so now that we have this, we can then do self dot logits is equal to self dot fc1 x, right? And let's look at our logits. Print logits dot shape. So notice here, we passed in and let's print x dot shape. We passed in a 128 by 784, which is a 28 by 28, and we're outputting a 128 by 10 because we have an output of 10. So you can see how the shapes line up, right? Basically, linear layers apply to the last dimension. So the last dimension here is 784 inputs, so this must have 784 inputs. The last layer here is, we want 10 outputs, so the last layer has 10 outputs. And that's basically how it works. So there we go. There were logits. And now we're going to do our log softmax. So remember, it's not just softmax, but it's actually the log softmax. So if we look here in our cross entropy loss, it's not just probability, but the log probability, right? So we can do x is equal to f. So f is functional. So we imported this at the very top. Let's just quickly look. PyTorch has basically these functionals that just let you kind of access their things very easily. So we're going to be using their log softmax function. It's just built right into PyTorch, so no big deal. Let's go back down. Here we go. F dot log softmax. We're going to do the output x dim equals 1. Why is it 1? Because we have 128 by 10. So let's go back here. We have a tensor of shape. Our output is basically like this. Right, we have some output that's 128 by 10, and we want to compute the softmax across each sample like this, right? So this is dim equals 0, this is dim equals 1, because this is a 128 by 10 tensor. So dim equals 0 refers to the 0th index, or the first index, and then dim equals 1 is second index. If you know NumPy well, then these axis manipulations shouldn't be too complicated for you. So yeah, we do this, and we have print x, and there we go. There's our outputs of our model, right? And then we can return x. Now, this may seem all well and good, except for one thing. So, except for one crucial thing, actually, this is actually wrong. It's not wrong because we're doing it. It's wrong because PyTorch is not expecting it. So let's kind of pull this in real quick. If you look here, PyTorch expects the raw logits. So PyTorch will do the softmax for you. It does it already inside the cross entropy loss, right? So the cross entropy loss computes the cross entropy between the input logits, the raw outputs of the neural network, and the target, right? The target is just our list of like, what is it? So it does the softmax, which means if we do the softmax right now, we're going to return a softmax, but then it'll do us another softmax on top of it. And this is a rookie mistake. I've seen this done a ton of times by a bunch of my students. So we definitely don't want to do that. So we want to return the raw outputs of the model and just like know that this softmax, this log softmax operation is happening. PyTorch is just doing it for you internally. And that's because they have to do something called a stable softmax, which there's basically some stability problems with softmax in the way it is. I won't go into it too much right now, but this should give you a general idea, right? General idea is what we're going for here. So this is our output. No big deal. Now, a quick problem is actually let's just go with it like this. We're going to keep this as simple as possible and build it up as we go. So we'll just get rid of that because we know it's not correct. Okay. Okay, good. So now we're going to do our training loop. So we've kind of we've tested our model. We see the input and output are the shapes that we expect it to be. So let's comment that out. And we're going to do training loops. We're going to do model is equal to fcnet. Optimizer is equal to, in this case, optim.atom. We're going to use the atom optimizer, like we mentioned, is just better. It seems to work best in most cases, so we're just going to go with that for now. But again, you should definitely test optimizers to see what works well in your scenario. We defined a learning rate ahead of time too. This is the stuff we defined up here, right? Yeah, so these are the things we picked. There's our optimizer. We then can do for epoch in range epochs, right? And we can print out epoch or training epoch, something like that. If we do this, it'll start at 0. So we'll just do epoch plus 1 so it's clear. It's fine. And now we're going to do losses. So we're going to create a list here. Losses is an empty list. And you'll see why we're doing that in a bit. We're going to do 4 images labels in train set. Print images.shape. Print labels. And let's do a break and a break. So this is what we expect, right? This is our stuff. And so what's the first step we do? Just like before, we're going to do model or prediction is equal to model. Actually, let's do this. Let's call it forward out is equal to model and images, right? So that's our print forward out. Right, so these are my current predictions of the model, whatever it may be. What's next? We need to do a loss. We're going to do loss is equal to the that loss function we defined earlier between what? The forward, out, and the labels. So print the loss. Okay. So let's quickly talk about cross-entropy loss. I don't want to do too much of an aside on this. We'll have another time where we'll dig into it. But again, let me pull back up the here, right? So our cross-entropy loss is basically the, here we go. It's the negative sum of our basically log probabilities times WC, right? So WC in this case is the weight, right? We don't have a weight in our case, so ignore it, right? We don't have that. It's going to be the weight is basically, this is if you have unbalanced classes, and we'll talk about this later, but for now, ignore WC. So it's just the log probability times the y value, right? What the true y value was. And so what does this exactly look like, right? The way to think about this, y is the target. Yeah, so the way to think about this is kind of like this. Let's pretend, right? Pretend our digit, we're passing a picture, right? We're passing in a picture of a 5, right? A 5, right? We're passing in a picture of a 5 to a neural network, right? To a neural network. And this is going to have 10 outputs, right? There's going to be 10 possible outputs, which means at the end, we're going to get a, when we do the, the softmax of it, we're going to get a probability vector, right? That looks kind of like this, right? It'll be probability that it's 0, probability that it's 1, ... probability that it's 9, right? The possible digits that it could be. So this probability vector may look kind of like this, right? So let's say we have this here. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So let's say the model's training a little bit. So it's already kind of learning that like maybe this is the probability vector. Or this is kind of what the probabilities look like, right? So this is my prediction. Now, what is the ground truth? The ground truth is 0 everywhere and 1 at 5, right? So cross-entropy loss is actually just a measure of the discrepancy between these two distributions, right? My true distribution is 0 everywhere and 1 at 5. And the predicted distribution is this thing. And so this error, this discrepancy, it's also known as the KL divergence, right? We'll dig into this later, especially when we get into variational autoencoders in the future. We'll definitely need this, but this is kind of your KL divergence term, right? If you don't know what that is, no big deal. We'll see later. But KL divergence is basically just the measure between these two distributions, the discrepancy between these two distributions, or the distance between two distributions. And cross-entropy loss is basically just another way to compute. The KL divergence is a portion of that cross-entropy loss term. So don't worry about it too much, but this is basically what the cross-entropy loss is measuring, right? So it's the log of the probability times the actual class that we want. So, okay. So now that we have that, now that we have all this, we can go back and wrap this up. So this is our loss, 6.847. And so just like before, we're going to do loss.backward, optimizer.step, and optimizer.zero thread, right? Just like we did before. Let me open this thing back up. Okay, good. All right, so we have this. We have everything we need. And all we're going to do is one thing here. So print loss, again, loss. Looks like it's not computing gradients for some strange reason. So let's take a closer look here. What we're doing here is logic. Oh, I see. We're just directly returning x. My bad. We need to return the logits. There we go. Yep. There we go. So now we can see we have this loss, and we have NLL loss backward. This is the negative log likelihood loss backward function. There we go. Sorry about that. So now we have everything we need. And so now when we have this loss, when we print out the loss, it kind of gives us all this information. We don't need all of it. What we really just need is the number. So we can do loss.item, and it'll just give us the number. And we can do losses.append, loss.item. We're going to store them up. And that's it. Yep. Okay, let's stop that. So now, at the end of every batch, we're going to do, or every epoch, we're going to do print loss. The loss is going to be np.mean, and it's going to be the mean of losses, right? It's going to be the average loss for this specific thing. And so that should give us, oh, let's also not print out stuff. Let's get rid of you. Right, so we're going to let it train. And you can see the losses 0.36, 0.28, 0.28, 0.27, 0.27. So not so bad, right? So you can see the losses decreasing. Good. So now that we have that, let's go ahead and compute the accuracy, right? So that's an important thing to be able to do. So we're going to do correct is equal to 0 and total is equal to 0. And what we're going to do is throw the model into evaluation mode. This doesn't matter for what we're doing right now, but this is just good practice. Before you inference a model, go ahead and throw it in evaluation mode. When we look at some modules later, they actually are affected by whether or not you're in training or evaluation mode, but for now, this is fine. We're going to do with torch.nograd, or inference mode. Either one works, nograd or inference mode. I think they're identical. With torch.inference mode, for data in test set, we're going to iterate through our testing data. We're going to then do, and not just data, but really for images, labels, and test set, we're going to do forward out is equal to the model for the images. We're just going to pass our images into our model. We're then going to do print forward out dot shape and break, right? So what we want to do, and we also have print labels, right? And so what we're going to do is just loop through each of the samples and see what the maximum is. And whatever's max, if it matches this, then we're good. If it's not, then it's incorrect. So we can do for label, or for, let's see, for IDX, I in enumerate forward out, print. So we're going to do print I and break real quick. So this is the prediction vector of the first thing, of the first one. And so what we want is the maximum one. So we're going to do prediction is equal to I np.argmax, actually no, not np, but torch.argmax I. Right? This is what I predicted. Oh, don't want to do it for all of them. Throw a break in there. This is what I predicted. Right? Whatever it may be. Okay, yeah, this is what we predicted. And so then we're going to do if torch.argmax, or if prediction is equal to labels I, then we can do correct plus equals 1, right? If my prediction, the max prediction, the max probability, right? Because whatever has the maximum logit will also have the maximum probability, right? They're the same thing. So whatever has the highest value, if it's correct, then we can go ahead and just add 1. And then we can do total plus equals 1. So we just keep track of how many samples we have. And we can loop through everything, and then we can do print accuracy is going to be, let's just round it off. So we're going to do round correct divided by total 2. This should be I dx. So we have a 92% accuracy. That's not bad. That's actually pretty good. Except for one thing, that's actually pretty bad for MNIST. MNIST, we should get like 97, 98% accuracy. So what are we missing, right? What are we missing? So now let's go back up to our model and take a quick look. All we did is take our data, flatten it, do a linear projection, and return it, right? There was never any nonlinearity that happened here. We never included a nonlinearity. So why don't we try to include one? So we have, a ton of these activation functions we can pick from. Let's just go with ReLU. It doesn't really matter. You can pick any one of them, and you'll probably get similar results because MNIST is a very easy data set to work on. So we're going to do f.ReLU, right? So now we do a linear projection, and then the linear projection is passed into a ReLU function, and that makes our logits. So now this is our model. So let's go back here. So let's let it train. Actually, yes, this is actually slightly incorrect. That is my bad. So as you'll notice now, our accuracy will have fallen. Why did it fall? Why has our accuracy gone down? Well, it is not proper to include an activation function on the output of your model. What do I mean by that? Basically, what we've done is hamstrung our model. Our logits, the raw outputs, can now only be between 0 and 1. Which isn't very helpful, or only be greater than 0, right? But otherwise it is 0. So this is not a very helpful thing to do. Typically on the last layer, we leave it as a projection. On other layers, we add in different activation functions. So let's go ahead and do that. We're going to do self.fc2. We're going to add a new layer here. fc2 is nn.linear. And first, this is 28 by 28, our input. What it outputs is kind of arbitrary now, right? We need to make sure, so we have a question mark here, and this will have to output 10. The second layer will have to output 10, but we have a question mark here too then. What we pick this to be is our hidden layer, right? We can pick this to be anything we want. Let's say it's 64. So if this model outputs 64, then the next, or if this layer outputs 64, then the next layer must input 64. That's the rule. Right, so whatever this outputs, this must input in the next layer. And so now what we can do is let's do x is here, and let's just do x here. And x is then equal to self.fc2. So what have we done? We took our input, passed it through this layer, which outputs, so it goes from 784 down to 64. So if we print x.shape, right? And let's just create that rand as torch.randn. 16 by 1 by 28 by 28. And then model is equal to fc net. And then model rand. So if we look at x.shape, right, it's 16 by 64. We passed in 16 by 28 by 784, but now it's down to 64. And then the next layer will input 64 and output 10. So now we have a stack. And that's exactly what's happening here. This layer is taking 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 inputs, and it's outputting 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 outputs. And so the next layer has to take in 9 outputs, and then outputs 9 again. In 9 outputs, outputs 9 again. But the last layer will be how many outputs we actually care about, the 10 that we need. And so what we've done here is made our model deeper. We've added depth to our model. And so this is now our model. Good, let's just comment this out so we can keep it for later, actually. So great, let's go ahead and train our model. Let's see how it works out now. So we can see the loss is definitely going a lot lower than before. Remember, the loss before got stuck around like 0.24, 0.25, something like that. But we can see the loss is decreasing. And now we are at 97% accuracy. So just adding a little bit of depth to your model gives, sizable gains in your performance, which is kind of cool to see. And we can make this whatever we want. We can basically just add a ton of layers. Let's say, let's add, that's probably too many. Let's just add whatever. XC2, XC3, XC4. All of these, let's say it's 64, and then let's say this is, let's say this goes from 64 to 128, and then we go from 128 back down to 64, and then we can just do this, add in the couple layers, FC2, FC3, and then FC4. All right, so what happened? We have a linear layer, we pass our data, reloop. Second linear layer, pass our data, reloop. Pass our data, reloop. Repeat this over and over again, and then the output will not have an activation because PyTorch will add the Softmax to it in the loss function, so we don't have to worry about it. Let's go ahead. Now, this won't be any better, right? This won't be a better model in any way, just because MNIST is already a very easy data set to train on, so no big deal. But yeah, we're training here. We got 5 epochs and right, so it's still 97. Didn't really improve anything, but that's fine, right? No big deal. This should give you an idea, right, of how we can stack layers in PyTorch. Good. So I know this was a very long video, but hopefully it gives you a kind of robust intro to PyTorch. But there is still one thing we have not talked about yet, and this is incorporating GPUs, right? So let me find the matrix multiplication image. So let's quickly take a look at this picture here. This will be kind of helpful for everyone to see. So if you look at this picture here, matrix multiplication is kind of a very parallelizable task. So if we want to compute C1 here, for example, right, that's going to be A1 times this A times B plus this one times this one, and that gives me this value. And then I do this for this second round, it'll be this row times this column. And then this one, it'll be this row times this column. And repeat that over and over again. Now, traditionally, if we implemented matrix multiplication, we'd have to write a bunch of for loops, right? We multiply this by this and then accumulate and then add them, and we'll have some other empty matrix that will populate the values in. No big deal. CUDA lets you do all of this in parallel. Basically, if each one of these 4 things are independent computations, there's no reason we couldn't do all 4 of them in one go. There's no reason to loop through them. We should be able to do all of them in one go if we can properly parallelize that. And to do this, they use thread blocks and stuff like that, which we'll maybe do CUDA another time. But for now, it doesn't matter, right? So for now, we don't have to think about it because PyTorch has already written very efficient and custom CUDA kernels for us to utilize for our own training. So let me go back here and just move this aside. There we go. All right, so yeah, let's take a look here. How do we use a GPU? So GPU acceleration is basically done to let us process our data and do all the matrix multiplications, because as we've seen, right, everything I've shown you so far is some W transpose X, right? We're multiplying some data by some weights. And if we're doing a matrix multiplication, GPUs are just way faster at doing these linear algebra matrix manipulation stuff than a CPU ever will be. Now, for the model that I did today, this very tiny model up here, you will not see, oh, why is it not scrolling? There we go. you will not see very big gains, right? We're not going to see very big gains here because this is just too simple of a model and anything can train it. But when we do big models like transformers, convolutional neural networks, stuff like that, like the difference in speed is enormous, like 1000x or even more, right? So it's important to be able to use GPUs. So how do we do this? First, we set the device. So if we do CUDA, that means use a GPU. If we do CPU, then that is use your CPU. If you do CUDA 0, this would mean if you have multiple devices on your GPU. So if we do, and let's do it down below, NVIDIA SMI. So this is my personal computer, and my workstation has 2 GPUs. You can see GPU 0, GPU 1. Each of them are A6000s. And there's some other information here that's also helpful to see, right? Like seeing how much memory your GPU has. This kind of determines things like the batch size and model size that you can train in. We'll talk about all this later when we start like building bigger models. But for now, this is totally fine. So what we have is 2 GPUs, and if I want to train on just this one, then I do CUDA 0. If I do want this one, then I do CUDA 1. If you want to train on multiple GPUs, I will have an entire section dedicated to kind of distributed training, like on Accelerate and some other platforms. But for now, this is, I think, okay. So let's just go with this. So your device is CUDA 0. So when we define, we do model as FCNet, right? This is my model. This model is currently sitting on the CPU, right? This model is sitting on CPU. But if we do .2 device, now the model is sitting on GPU. It's been moved to the GPU. I don't think this model is big enough to cause, so we can see it's 608. Let's see. Oh yeah, we see it went up a little bit, 873. So a little bit of GPU memory was used to move this model to that device. Right? Everything else stays the same, by the way. Optimizer is equal to optim.atom model. Actually, I can just go ahead and just copy what we did before because it is exactly the same. Here. I'm going to grab you and just stick you right here and just swap that up. Great. So our model's on the GPU. We define our optimizer. We have all our stuff, everything's ready to go, and we're going to run it, and amazing, we have an error. And this is a very typical error you're going to see when you're working on stuff. It just happens by mistake. Maybe something's wrong in your model, maybe, anything can happen. So we're saying expected all tensors to be on the same device, but found 2 devices, CUDA 0 and CPU. What this is saying is that it's trying to do an operation between 2 tensors, but one of the tensors is sitting on the GPU, and the other tensor is sitting on the CPU, and so they can't interact. All your tensors have to be in the same device before an operation can be made. And so here, when we do, when we pass data, notice it's breaking on this line, right? When we're passing data through our model, it's not working. And why is that? It's because our images and labels are still on the CPU, but our model is on the GPU. So we just need to fix that. We can do images is equal to images.to device, right? We're going to move our, all tensors have this .to operation, by the way, and then labels is equal to labels.to device. That's going to go ahead and move our labels over. And now we should be golden, right? It's just going to quickly loop through all of this. No big deal. I wonder if we can see like, let's see, NVIDIA SMI. Yeah, so a little bit more GPU memory is being taken, mainly because it needs to store the like the things for momentum and stuff. So there are some more weights, some more values being stored on the GPU, but there we go. But we should get the same result regardless, right? So this obviously was not much faster than training on the CPU, but again, that's just because our model is very, very simple, and CPUs have gotten very fast in the last couple of years. So good. Last step is adding in a validation loop. So what did we do here? We, when we trained our model, right, we trained our model here, and then we evaluated our model down here. That's not recommended, right? You actually want to evaluate as the model's training, like intermittently. A typical way to do this is like train for, if you want to train for 5 epochs, train for 1 epoch, then evaluate, then train for 1 epoch, then evaluate. Just evaluate as you're training every once in a while. Then you can keep track of how the model's doing, and you can test for something very important called overfitting, which we already talked about. So let's go ahead and kind of see that. So um, I can actually just go ahead and copy this in because this is no different than anything we've done so far. So we have our model, we have our FCNet, we're moving into the device, our optimizer, how many epochs we want to train for. And what I've done is create some two lists. I have my training losses and my validation losses, right? And this is going to be, for every epoch, what is the average loss for that training and what is the average validation loss? So we'll kind of create some lists to store those. What we can do next is iterate through our epochs. There we go. And this should be epochs plus 1, actually. So there you go. And now inside every epoch, we're going to just store up, right? What is my loss for one of the loops? So we're going to loop through our data. We're going to grab our data. We're going to do our optimizer. We're going to compute the loss. We're going to store the loss, loss.backward optimizer.step. Nothing fancy. And then we're going to store those in here. And then the next one, again, we're going to loop through, do exactly the same thing, but we have a model.eval to set it to evaluation mode. Doesn't matter for this specific model, so it's okay. And then with torch.nograd, or you can do inference mode, they're identical, right? So we have both of those. Again, same thing. And then we're going to average up what was my average training loss for this epoch and what was the average testing loss for this epoch, and then store that in our outer lists, right? Just like that. And then we'll just print them out just to see how things are going. And so let's start this run. This won't take more than maybe a minute or so. But there's a reason I'm doing this, and that's so we can see this. Keep an eye on the loss values and see what happens. Notice that our training loss is now at 0.8, 0.7, 0.6. It continues to decrease how our training loss is going, but our validation loss is stagnant, right? Notice it's not even stagnant, it's actually increasing. Like it's getting worse and worse, which isn't helpful, right? The validation data set exists for us to evaluate how the model performs on data that the model's never seen before, right? That's the whole point of it. If you're going to train a model, you want it to work in the real world. And in the real world, there's going to be data that your model hasn't seen. So if your model's not performing so well on the validation data, but performing well on the training data, you know exactly what went wrong. You are now overfitting. And so we can do x is equal to list range 20 because we did 20 epochs, and then plt dot plot x and training average loss, and the label is going to be training loss, right? So there's my training loss, right? That's how I see I can see as the epochs are increasing, my training loss continues to decrease. So that's helpful, except when we plot the next one. This will be the, not training loss, but the validation average losses. And this will be my validation loss. And we can do plt.legend and plt.show. And this is a very typical thing you'll see. Notice how we're training and training and training, and our training loss continues to improve, but our validation loss is not. If not, it's actually getting worse. So this is a very clear sign of overfitting, and it's not good, right? So this is why it's important to kind of intermittently check your validation curve, see how it's going, compute the validation, or compute the loss on the validation data just to see how it's going. But yeah, this is basically it. This covers my intro to PyTorch, a very long-winded and extensive introduction to PyTorch actually, but it should give you an idea. So I'll just do a quick wrap up here just so we cover the main ideas, the things I want you to take away, right? PyTorch works on multi-dimensional matrices known as tensors, and tensors are everywhere. All data is basically representable in some sort of a tensor. And PyTorch, it's basically a NumPy on steroids. It does NumPy computations on the GPU, so it's extra fast because a lot of these matrix manipulations that I've been explaining so far are very parallelizable. We can easily do them on a GPU very quickly. That's the whole point of it, right? We can do this on GPUs quickly, which is why PyTorch can be trained on GPUs. It also performs this whole AutoGrad mechanism, which again we saw isn't anything but basically a depth-first gradient accumulation algorithm, right? It does basically something along these lines. So that's good. What else does PyTorch do? Let's check here. Yeah, so we did a linear regression example, and we derived linear regression, the actual formulation for it, and I showed you that linear regression has a closed form solution, which is great, except this matrix inversion, right? The expensive portion of this entire computation. So instead of doing that, what if we use stochastic gradient descent to actually train our models? And that's basically what all this is doing. PyTorch will train your models, taking where it computes gradients and then takes little steps in the right direction. That's the entire purpose of PyTorch. We can do the same thing for classification tasks. We can use binary cross-entropy loss, which is what we use in the case of binary things. If we have more than two things, then we can move on to categorical cross-entropy loss, which is what this MNIST data set was, right? And we talked about how PyTorch, or how neural networks, are really just a stack of linear projections, right? It's just a stack of linear layers, which is just multiplying data by some constant, but it also including some non-linearity in between those things. Because if you just have a stack of linear computations, then the relationship you can ever only express is a linear one. But by including some non-linearity, regardless of what it is, right? Like ReLU or sigmoid or any one of these things, right? We have, a variety of, there's even more, there's way more than this, a variety of these activation functions, you kind of get these kind of results. Oh, that shouldn't be in there. 1 second. That must have just gotten in by a typo and I was copy pasting stuff. That's okay, just ignore it. All right, and then we've trained some models. We computed the accuracy. We saw that as we increased the complexity of the model, the accuracy went up, which is good to see. And we saw how we can easily move some of these computations to the GPU, which is also exciting to see. I'm sorry, that's kind of a wrap up of this entire section. Next up is data sets and data loaders. Hopefully I'll get to that in the next week or so. But yeah, thanks for watching and let me know. Give me some feedback if this works, if this is helpful, if I was too in depth. I know I covered a ton of stuff, but yeah, I'll see you in the next one.